Yes. We can be heard now? No?
I'll just say, oh no, wait. Do you log into the website?
Yes. Can you hear it now?
Can you hear us?
Yes.
Okay, guys. Back to introduction.
We may have been muted earlier,
Okay.
but
Sorry.
I think we're good to go now. Welcome everyone to this diploma stream. Three things. We have transformations and functions. We got trigonometry, both 1 and 2. We got perms and toms last. This is only for the diploma, so this will be no IB content, only like the very basic of what you will need to know to go into the exam and ace that. And so we're on a tight schedule. We only have 4 hours. We're not gonna go over any full length problems. We're gonna teach you everything. We're gonna get you like to learn as much as you can without doing any like actual problems. However, you are free to ask any questions you may have in the chat. We'll try to answer those as well as we can. Yes.
Good.
So the 4 units we're going to be doing today are functions and relations at 12:15, and then we're going to do trig at maybe close to 1, or 1:30, and then afterwards we're going to do perms and cons around like 2:45. So if you have a particular unit that you might want to review, you can just like come back later. But of course, this live stream will be available to you after we are done streaming, and so you can always just refer this back to the live stream when you're actually studying for the diploma. Cool. So we'll hand it over to Edward.
Okay. So, our first unit we're going to be discussing is transformations. So the first thing we're going to discuss in reference to transformations is function notation. So function notation is when you write a transformation in this form. Y equals A, B, oh shoot, sorry, times f of B times x minus C plus K. Sorry, this is H. Sorry, guys. So first thing we're going to discuss is what exactly do each of these parameters do. So the 4 parameters we have here are A, B, H, and K. So we're going to start with A because it's probably one of the easiest. A, in this case, is just the vertical stretch. So the vertical stretch is basically like a certain distortion. You use the graph vertically. So for example, if you have a graph that looks like this, a vertical stretch of factor A would make it something like this. Our next parameter that we'd like to discuss is B. So now B is a little bit more complicated. It represents the horizontal stretch. But the factor to which its stretch is actually 1 over B. It's not B. Let me get this. Factor of stretch. So basically what this would look like is if we have a function f of x that looks like this. If we have a horizontal stretch with b equals 2, so b equals 2, the horizontal stretch would be 1/2. So what does this look like on the graph? Well, if the horizontal stretch is less than 1, we're actually squishing the graph. So our new graph would look something like this. F of 2x. And now if we have something like b equals 1/2, then our horizontal stretch would be, our horizontal stretch would actually be 1 over 1/2, because the horizontal stretch is 1 over b, which is just also equal to 2. So now if our horizontal stretch is larger than 1, what we're actually doing is we're stretching the graph out. So our new graph would look something like this. So now we're going to move on to our translations. Our translations, specifically h and k. So we're going to start with h. H represents the horizontal translation. Horizontal translation, yeah. Is it too small? Oh. Sorry. I'll write bigger. Trans H is the horizontal translation. So for example, if we have h equals 2 to a graph with y equals f of x, the graph of y equals f of x minus h. Oh, shoot. Yeah, okay. Would shift it 2 units to the right. 2 units to the right. So it looks something like this. On the other hand, if we have h equals -2, then it would actually go to the left. So y equals f of x. So this would actually be -2. This is +2. And then, yep, y equals f of x plus 2. So one thing you have to be careful of is, in this case, we have y equals f of x minus 2. And a lot of students think that because there's a minus, you're moving it to the left. But that's actually not right. Because in function notation, you need to account for the minus that's already here. So if you have x minus 2, you'd actually be shifting it to the right rather than to the left. And for plus 2, a shift of +2 would actually be to the left. And our final parameter is k. This one is actually quite easy. It's just the vertical translation. So the vertical translation is pretty straightforward. It's just moving it up or down by k units. Move up or down by k units. So in this case, we can have k positive. K positive would mean a shift upwards. So something like this. And then obviously, if k is negative, what will end up happening is the graph will be shifted down. Okay. I think that's it for function notation. So we'll move on to our next topic, which should be replacement notation. So replacement notation. So actually, as I'm reviewing replacement notation, I'll also talk to you about mapping notation. And then at the same time, I'll also have a column that represents transformations inwards. So replacement notation is literally like if you have a function y equals f of x. Sorry, can they see that? Okay. If you have a function y equals f of x, replacement notation, if I write like x goes to x minus k, that literally just means take every occurrence of x in the original function and just replace it with x minus k. So y equals f of x minus k would be the result here. So now we're going to go over all of the different replacements. So first of all, we have x goes to x minus k. So actually, what this represents in terms of transformations is a shift to the right. Right by k units. This is pretty straightforward as we've discussed before. And then also at the same time, we have if x goes to x plus k, that's just a shift to the left. Shift to the left. K units. So now for mapping notation, what we're going to do is we're going to take whatever we see in the replacement notation and we're going to reverse it. So mapping notation literally just represents what each coordinate goes to. So our original coordinate is x, y. By replacing x by x minus k, what we're actually doing is we're shifting. Oh yeah. By the way, k is greater than 0 in this case. So mapping notation is basically taking the coordinate x, y and moving it, right? So this is the coordinate on the original graph, and then we're going to move that to another coordinate, and that new coordinate is called the image point. So for this case, we're going to shift to the right by k units. And what does that do to the x coordinate? Basically, what we do to the x coordinate is we shift it to the right by k units, and we just add k. Now, for a shift to the left by k units, we're going to do the opposite of that. We're going to subtract k from the x coordinate because that moves the image point to the left. Now for our scalars. So x goes to ax. Oh, actually, bx would be a better variable to use here. So a replacement of x goes to bx, as we've discussed before, is a horizontal stretch, right? So the horizontal stretch we're discussing here is basically a horizontal stretch of factor 1 over b, not b. So for our mapping notation in this case, we would have x, y goes to, well, if we have a horizontal stretch of factor 1 over b, what we're essentially doing is we're squishing the x coordinate by a factor of b. So we just divide the x coordinate by b. Next thing, we have our y-coordinate. Now, for our y-coordinate, the replacement notation is pretty much the same. We have y goes to y minus k, means a shift up of, oh, this should be, no, h. I'll just use h. So shift up, so a shift up of h units, right? And then y replaced by y plus h is a shift down of h units. Okay, so basically in mapping notation, it's literally the exact same as our transformations to the x-coordinate. For this one, if we shift up h units, we're just adding h to the y-coordinate. So xy would go to xy plus h. X y minus h, because this one is a shift down. Lastly, we also have the horizontal vertical stretch. So y goes to ay. This is just a vertical stretch. Factor 1 over a. And basically, if we have a stretch of factor 1 over a, we're kind of like scaling each of the y-coordinates by a factor of 1 over a. So we just divide the y-coordinate by a. Okay, one last thing that is pretty important is whenever you say you have a horizontal stretch or a vertical stretch, you also have to say what axis it's about. So if you have a horizontal stretch of factor 1 over b, that's just about the x-axis, y-axis. And if you have a vertical stretch, it's about the x-axis. And the reason they're opposite is because if you have a graph like this, and you're stretching it vertically, the axis to which you're doing it is the x-axis. It's not the y-axis. And then same thing for, this one is y stretch, x stretch. Stretching it about the y-axis. So another thing, Okay, yeah, sure. So now we'll have Jack discuss reflections and inverse.
Okay, so really quickly, what you gotta know about replacement notation is that instead of writing it the same way in which you would write like the other function notation, it actually looks something more like this, where you have ay us h equals bx us k. So the reason or it should be minus usually. And so the reason we do this is so that you don't get confused with like the actual function notation, because when you write it as an equation like this, you can then transform it into the other notation by like adding h and then like dividing by a. So that's how you get the different notations and how to get the transformations to work. Okay, and then one last thing about reflections is that about stretches is that when the a or when the b value is negative, what it does is it makes a reflection about the axes. So what does this look like? So let's say you have a function that looks something like this. And now you have our value of a over here. If it's negative, then obviously we go from a y point goes into a negative y point. Let's say a was -1. What that does is it takes each of these points and then it puts it to the opposite side of the x-axis. So instead of looking like this, the transform graph would look more like that. No. Like that, yeah. And so that's how reflections work, is that when you have your a or b value as a negative number, it just takes the entire graph, reflects it over the axes. And it takes all the coordinate points and then transforms them to like the negative of what it was before. What's after? Okay, next up, I think I should also talk about the inverse. On the Alberta Diploma, the inverse is not going to be paired up with any other transformations. And so what that means is that if there's an inverse problem, the only transformation present will be the inverse, also called a reflection over the line of y equals x. So what an inverse really is it takes every point, let's call it a point of like x and y, and it just flips them around. It flips them so that the point goes into y, x. And so typically reflected over x over y equals y. And one way to graph this when it tells you to sketch it is you just like take points and then like take points that are in the form of x, y, and then place them into the new coordinate of y, x. I think another part of inverse is if it will tell you to get the equation of the inverse of a function. And so all you have to do in that case is once again switch out the x and the y. So consider that you have a function that is, say, like f of x plus like a plus like k or something. When you want to get the equation for the inverse, all you gotta do is switch out the x and the y. So x equals f of y plus k. And the f of y is what the inverse is. And then you want to solve for f of y. I don't know. And then you just get f of y is then equal to x minus k. Yeah. Yes, that's how you do it. And so the other part of, and so that's how you get the equation for an inverse, is you swap out the x and the y, and then you solve for the y again after that. What? I don't know. I need a proper function to like give a better example. So next, not enough. Okay. Next part is on the order of transformations. So the proper order of transformations when you're trying to sketch a graph or you're trying to move a point is you want to do your stretches and reflections first before you do any translations. So why you want to do that is, okay, so I'll just give like an example of why you would do that. So let's say you have a point of like over here. If you were to translate it upwards before you stretch it, the stretch is like, the translation is pretty much like doubled and you do the translation twice. Whereas if you go up to like this point, and then let's say you stretch it after, it goes like even higher, or maybe over here. However, you want to do the stretches and reflections before, because those are like I don't know, the transformations that kind of take priority. And this way, you can see that if I were to stretch it by like double first, maybe it goes here, and then I move it up, and the final point is here. And so there's like quite a difference. So you have to pay attention to that to make sure you do your stretches and reflections before you do any other actions, I guess. The other thing is, how do I transform this into words? Let's say you have a coordinate point and it tells you to like stretch it by a certain amount and then translate it by a certain amount. In that case, we want to use replacement notation, and we do the replacements in the order which the problem gives us. So let's say it tells us to stretch it by like 2 about the x-axis, and then it tells us to translate it up. Let's say 1 unit. In that case, we take our original equation, which was y equals x, and we want to replace it. So we do the stretch about the x-axis. So we go into 1/2 y equals x, and then is translated up 1. So we want to, when we translate up, we're replacing y with y minus 1. So we go 1/2, and then y goes into y minus 1. If it gave us the order of transformations the other way around, let's say we wanted to translate it up first, and then we wanted to stretch it by 2, then we would have to reverse the order we do the replacements. This means that instead of doing it like this way, do I have space? Yeah. The other way would be to start with y equals x, and then first you translate it up 1, so y goes into y minus 1. And then you want to stretch it by 2, so that means y turns into 1/2 of y. And so the 1 is not actually like part of the y, so you don't do the 1/2 transformation on the 1 in this case. You would only do 1/2 of y minus 1 equals x. And so those are the differences when you're using replacement notation based on whatever the question gives you. After you have your like replacement notation equation finalized, you can then transform this into a proper function of y equals something about x. So let's take this equation. All we have to do is isolate the y, or solve it so that y is on one side and then everything else is on the other. So if we do this, it just turns into y minus 1 equals 2x, and then y equals 2x plus 1. And so if we see this, we do see in fact this is a stretch about 2 about the x-axis. We see the a here is 2, and then translated 1 up after that. Next part then is onto how to sketch all of these. Edward and I already like went over some basic sketches of if you have a single transformation, but I think we also have to go in for multiple transformations. This is where the order of transformations also really matters. So let's say we have a function that looks something like, maybe like this. Once again, you have to pay attention. You have to do your stretches and reflections before you do any of the other transformations based on like the function notation. So let's say we do the same transformations of like stretch it by 2 about the x-axis, translate up by 1. A stretch by 2 about the x-axis, once again, is just the distance of any point from the x-axis is going to be doubled. That means this point over here is going to be twice the distance away from the x-axis and go up there. And we call it a stretch because if you do the transformation onto every single point, then it looks like the entire line has like stretched or elongated to fit that transformation. After you've done that, the next part is to translate it up 1. And so translations are a lot easier to do than stretches. Because for translations, all you gotta do is take the like kind of picture that you already see and then move that up by 1. So maybe let's something like, I don't know, like that. And then I think the last part of this is how you would sketch a reflection. One easy way to like keep this in order is to do reflections and stretches separately instead of trying to do it all as like one single transformation, because that's like too much to think about. So let's say we have a reflection about x-axis again. I'll draw like another thing. Let's do like, I don't know, like that. So the first thing you want to do is reflect it about the x-axis. What this means is that however far this point is from the x-axis, it's going to be the same distance away, but it's going to be below it. So this point would go down to here. And then once again, if you were to do this onto every point, it would look like the entire line has like done a mirror or a flip or a reflection about this line. And so our new equation would look something like that. After we've done the reflection, we can then do the stretches the same way we did them before. We take every point, however far it is from the x-axis, is going to be like twice that length away. When we do that to the entire line, it looks like the line or the graph has like stretched itself. And then translations, again, are pretty easy to do. All you gotta do is take the image of like what the graph looks like and then move it slightly to the right, slightly to the left, or slightly like up or down. And then what next thing that's a bit later, that we learned a bit later, is how to do composite functions and how to do operations on functions. So let's start with operations on functions. So there are four basic operations that like we learned very early on. It's just addition, subtraction, multiplication, and division. But when we learn them, we usually only do it with specific numbers. What we do now is we want to do these same basic operations, but on entire functions. So let's say we have two different functions like fx and gx. Let's just do like x and like, I don't know, x squared for simplicity. All it is the same thing. If we want to do addition upon these two functions, all we do is add them together. All we do is to put the x and then plus x squared. Same thing with subtraction and multiplication and division. It's the same thing as like basic operations. It's just that instead of using numbers, we're using like variables as well. So the hard part about this is trying to graph the functions or trying to sketch them out. So if you take x, the function will just look like that. It'll look like that. And then x squared will look something like that. Sketching these functions are a bit harder because like there's so many points and it doesn't look the same all the way around. So let's do like multiplication. Multiplication is really easy for this one. How do we sketch it? Well, we first do the multiplication to find our new function. So if this f, g, oh, okay, that's the times by the way. So we first want to find like the actual function for like them being multiplied together, and then once we have that, we can make the new sketch of x cubed, which is just looking something like that. So one way to do this like really easily is if you want to use your calculator. Actually, it's fine. So with your calculator, you can have like upon the graph, you can like enter anything. So let's say I have the f of x and g of x as x and x squared. Is it echoing? Oh, I think it's just my problem. That's okay. So what you want to enter into this like y1 place is you don't even have to find what the function multiplied by itself is. You just take the 2 and then like just enter it as that. And then when you graph it, it like automatically calculates it and does it all for you. Let's take x squared plus x, for example. If we just do it like, if we just look at these two graphs and try to like add every point on every other point, it's gonna be kind of hard to do. What? However, if we take our calculator and we put it in as just x squared plus x, and we can do this with like any function no matter the difficulty, we get like, oh, Alan put in some more functions. We get the graph pretty easily. It's the black one over here. There's one last thing that I should talk about in operations of functions, and it's that the domain of the new function made by the operation is the same domain as like at least as restricted as like the most restricted initial function. So what does that actually mean? It means that if we have functions that are like this, and then another function that's like that, the domain of the combined operation is the same as the domain of both of them together. It's the same as like the common domain. So in this case, on the first graph, the domain is only on the right side of the y-axis. It's only restricted to x is greater than or equal to 0. And on the second graph, the domain is x is less than or equal to 0. So when you do an operation on any of the points over here, except for like this middle 0, 0, if we try to do any operation, let's say addition, we have this point over here, but then on the other side, on the other function, there's nothing there, like there's no such point. And that means that there is no way to do addition if there's like only one number. And you can't consider it as 0 either, you can only consider it as like not defined. So what that means is that when we try to add these functions together, the result is also undefined. And so if we try to add this function with that function, the resultant function is only like the domain of the common domain of the two of them, which is going to be like the middle 0, 0 point. And even though there's like a line over here and a line over here, it doesn't matter because on the opposite function, there's no such line. Is there anything else? Oh, opposite. Okay. And then last one here is another thing, and probably the last thing you have to do with like general functions, and it's composite functions. So what a composite function is, you have to graph them. Yes. Oh. Okay, so what a composite function is it's not a basic operation, it's like a function of a function. What does this mean? Let's say you have f of x is equal to like x minus 2, and then g of x is equal to, I don't know, x squared. The composite function can be either f of g of x, which can also be written as f with the circle thing of g of x, or it can be the other way around. It can be g of f of x, which can be written once again as like with the circle thing, g of f of x. What this means is that when we take a number x, let's say 1, we first put it into the inside function. We first put it into gx on the top one. And then once we put it into gx, we have a new number. Let's say we take the point of 1. If we take the point of 1 and we put it into gx, we have g of 1 is equal to 1 squared, which is equal to 1 again. And then we have this new value, and we put this new value into f of x. And we still have f of x is 1 minus 2, which is negative 1. So one way we can write this out is if we take the first one again, as we replace the f and the g of x into what the functions actually are. Let's take the first one. G of x is equal to x squared. So we have replaced the gx with x squared, and we still have f of x squared. Now we can take this x squared and then take this to put into the x of f. So this will look something like x squared minus 2, and that's what you get as the composite function. What if it was the other way around? We do the same thing. We take f of x, which is equal to x minus 2, and we have g of x minus 2. Now, g of x is x squared, and so this is the part that can be kind of confusing sometimes, is you want to take the entire thing as the new x instead of just like the old number. So g of x minus 2 is not equal to x squared minus 2, because that doesn't actually do anything. But it's actually equal to x minus 2, and then you take the entire thing to square it. And so that's how you get the equations of composite functions. Now, the last part is, I'm actually not certain about this. Disclaimer if I'm wrong. You might have to sketch composite functions. So there's two ways to do this. One of them, once again, find the equation, and then with your knowledge of transformations, you can then graph that equation. The second way to do it is once again using your calculator. If you use your calculator, you won't actually have to find the resultant equation. All you have to do is like take the f of x, put it in brackets, and then do like g of x on top of that. Oh, I don't have a calculator right now. That's okay. That's okay. One last thing is, what if it gives you a graph instead of an equation of the functions, and you don't know the equation of the graphs? This happens a lot because sometimes there isn't actually any equation. They just give you like a random bunch of lines and tell you to add things up. So let's say you have two graphs, one of them which may look like that, and then the other maybe like, I don't know, something like that. When it tells you this, they're not gonna expect you to sketch the new graph because there's like so many different points and stuff that is kind of impossible to do. But what you can do, and what they will ask you instead, is take a point of like x equals 2. If we take like x equals 2, what is f of g of 2? So let's look at 2 right here. Let's say this point is like 2 and minus 4. And then if you want fx, gx, and if you want to get f of g, oh, maybe not f of g, g of f of 2, remember that this is equal to g of f of 2. And so we found over here on the graph, we can locate the point and find that f of 2 is equal to negative 4. So all we have is g of negative 4. Now that we have g of negative 4, we do the same thing as before. We take the minus 4 point as the x. We go on to the second graph, and we try to search for, where is this point at? Let's say it's over here, minus 4 and 3. So g of minus 4, if we're given that point, is simply equal to 3. And so now we can find that g of f of 2 is equal to 3, and that's usually how they will give you the problem. What you have to remember, especially in these composite functions though, is that you don't read it from left to right. You can't take the g of the number first and then the f of the number after that. Instead of thinking it as something to read from left to right, you should break it down into this part and think of it as there's brackets on the inside that you have to do first. You always have to do like the second one, or the one most to the right, first, because you need that value of like f of x to put into the g and to put into the other function. Is that it? I think that's it. Time for Alan. talked about polynomials.
Okay, so basically Jack just went over a lot of the transformation stuff, and also Edward as well. So there's quite a few number of special functions that you need to know for the diploma. So first one we're going to talk about is polynomials. So we're just going to go over the quick definition of a polynomial if anybody needs to review that. So basically what a polynomial is you just have a different, you have a bunch of number of terms that are essentially raised to like an integer power. And so the actual definition is something like this. So you have f of x equals and then some sort of constant like in front of the leading term, and then you have x to the power of n, and then plus like some other constant like a n minus 1, and then you have like the next term, and then so on until you reach essentially x0, which is 1. And so you have here just the constant term, which is a0, right? And so here basically you see all these n's are integers, and also basically there's a bunch of these coefficients. So one thing you need to know for polynomials especially is knowing how to do synthetic division. So I'm sure we've all learned that you can divide things normally with long division. So let's just say I take a function, like a random function like x minus 4x plus 5. Okay. And then let's say I want to divide this by, let's say x minus 1, right? So this is just normal long division. And so what we're going to do is we're just going to follow the process. So up here, we're going to try to make this x match the x squared, right? And so we have x, just like so. Subtract over, we got negative 3x plus 5. I don't think it matters. And so, and then you have x minus 3 here. And so now you have negative 3x and then plus 3, like so. And then now you'd get a remainder. So 5 minus 3 is 2. And so now we have the remainder 2. Now, if we want to express this in terms of like actual notation, this would be x squared minus 4x plus 5 equals, and then you have x minus 3, and then plus 2 over whatever we're dividing with. So I think x minus 1. Yeah. Oh yeah, you're so right. This is x minus 1 here. Yeah. Okay, so this is essentially what you do in long division. Now, as you can see, it kind of wastes a lot of time. Now, in the diploma, you have 3 hours, which is like way more than enough for you to double check with both long division and synthetic division. But sometimes it might require you to do like find a certain step in the synthetic division process. So I'm just going to demo what synthetic division actually looks like for you. Give me 1 second. So if we do that same equation, right? So we have x squared minus 4x plus 5, just like so. Now, what synthetic division is we just take all the coefficients here, and then we write it out like this, 1 minus 4 and 5. And then what we want to do is we want to just write the factor of what we're dividing with. So if we're dividing with x minus 1, we essentially just put 1 right here, because like if you substitute 1 into x minus 1, you get 0, right? And so essentially what you do in synthetic division is you just keep on adding whatever two numbers you have like in a vertical column, right? And so here, you just 1 plus 0 is 1. And then every time you move it up, you just have to multiply it by whatever you have on the left side, okay? And then so you have 1 times 1 is equal to 1. Here you get negative 3, right? Because you add negative 4 plus 1 equals negative 3. And then what you do is you have to do 1 times negative 3 up here. And then now you just do 5 minus 3 equals 2, right? And so notice we got the same remainder. Here, this is going to be the remainder of whatever you're going to be dividing with. And yeah, so essentially you can see that long division and polynomial and synthetic division are basically the same. It's just that sometimes it might require you to do synthetic division instead. So yeah. Okay, so we're gonna next talk about one really important thing that you have to know, which is rational root theorem. So what it essentially is sometimes you get a really bad polynomial, and I say bad as in it's really hard to immediately know what can factor it. Okay, so let's say you get a really questionable polynomial. What is it? 2x cubed minus 11x squared, and then plus 17x minus 6, right? So when I look at this question, let's say I'm on the diploma, I look at this question, I have no idea what's going to go into it. So what I do is I think about the rational root theorem. Okay, so essentially what that means is all the factors that like all the factors of this polynomial equation, essentially, let's just say it's like it has to be a factor of the last term, which is -6, over a factor of 2. Okay, so essentially we're going to test all the values that match with whatever is here. Okay, so here essentially we have, let's just say -6/2 is -3, so we can maybe try this one. We can try -6/1, which is oh, -6, thanks. Okay, and then we also have 3/2, which is it's like this. We also have we also have 2/2, which is 1, and we also have 2/1, which is 2. I hope that is enough. And also, what you notice is like when it means factor, it also means like it can be positive or negative, right? And so here it's actually plus or minus for everyone. So you essentially, under the rational root theorem, you'd have to test here at least like 10 different values to see if they're a factor of the original polynomial. Okay, so essentially, in order to do that really quickly, because you don't really want to do synthetic division over and over again, because like who wants to do that, right? And so what you would do is you would use the factor theorem. So essentially what that means is when you plug one of these numbers into the equation and it equates to 0, that means you know that's going to be a factor of the polynomial equation. Okay, so essentially, let's just say we're gonna plug in the value x equals 1/2. Yeah, actually there's 1/2 here. So we're going to plug in the value x equals 1/2 into this equation and see what happens. Okay, so we're going to do 2. We're going to try f of 1/2, just like so. And so this is equal to 2 times 1/2 to the power of 3, okay, minus 11 times 1/2 to the power of 2, okay, and then plus 17 1/2 like that, and then minus 6. So we're going to just do a little bit of simplification magic. Here we have 1/4 minus 11/4 plus 17/2 minus 6. So we have essentially all equal to 0. Okay. So what this means is that 1/2 is actually a factor of whatever this is. And so if we were to write this, we'd keep going as in we'd probably do synthetic division. So we would divide this by, let's say, like 2x minus 1, because that gives you x equals 1/2 here, right? So you would know that this is a factor of this polynomial right here. And yeah, so that's basically how you would apply factor theorem and the synthetic division stuff all together, the rational root theorem. And so another really similar theorem, but it's also kind of important, is let's say you try to plug in a number, but it doesn't give you 0. So let's say I plug in the value x equals 5. Okay. Now whatever 5 is, when I plug into this value, it's not equal to 0. Now the actual value that you get is actually the remainder when you divide it by x, the equation x minus 5. So if you take this and divide it like over here by x minus 5, the remainder, whatever remainder you get is going to be the value when you plug in 5 in this equation itself. So there's actually a really neat calculator trick you can use during the diploma. So what you can do is you can just try to graph the original equation, right? So we have 2 to the x cubed minus 11x squared plus 17x and then minus 6, right? So here we just have it graphed like so. And then what we do, right? So as soon as we plot it just like so, we can just do trace, and then we can trace whatever value it is. So we're trying to divide by x minus 5 here, and looks like the y value is actually y equals 54. So it looks like that's going to be our remainder when we divide by x minus 5. So yeah, so that's how you apply it. Sometimes the diploma might ask you for like, what's the remainder when you divide this function by this function? And so this is a really quick way to do so without having to input everything into your calculator and so on. Cool. So next we're going to talk about some key components of the polynomial function itself. So this is what I'm talking about is like specific terminology you might need to know, because sometimes they might ask you, okay, what is the constant term of this polynomial? And so you would have to know exactly what it's talking about. So let's have an example where it's x minus 1 times 2x plus 3, right? So a simple polynomial. Now, the roots of this polynomial are, as you can see, x minus 1 equals 0, so x equals 1, or x equals negative 3 over 2. So these are the two roots to the polynomial. Here, the constant term and all the other stuff, you need to expand this polynomial out. So it would be 2x squared plus x minus 3, right? And so the constant term here is just the negative 3. This is the constant, right? So that's the constant. And you have the leading coefficient. So leading coefficient is just this one right here. It's like the most, it's the coefficient attached to the power of x that's the greatest. And then afterwards, the degree is just the power that's the greatest. So here the degree is 2. Okay. And then, so intercepts we've already given. So here we have the x-intercepts, which are x equals 1 and x equals negative 3 over 2. Okay. And then so here we also have to, in order to solve for the y-intercept, we just set x equal to 0, and then we solve for whatever point of y we have. So if we do that, we have negative 1 times 3, so y equals negative 3 for the y-intercept. So when it asks for x and y-intercepts, you'll probably write it like this. So x-intercepts, this is what generally people will be looking for. So you just write it x-intercepts, and then you would write the actual coordinates. So here x-intercepts are like 1, 0, and negative 3 over 2, 0. Okay? And you also have y-intercepts, just like so. And then you have x equals 0, and then y equals negative 3, which we calculated before, right? So in terms of what this looks like, we'd also sometimes be asked for domain and range as well. So in general, for polynomials, it's usually just x belongs to a set of real numbers, because if you think about it, it doesn't really, there's no value for x, which makes this function not exist at any point, right? And so usually domain is just x belongs to a set of reals, just like so. And then you'd also have range as well. So usually you would try to find the you probably honestly just graph it. That's probably the fastest way you can do it. Sometimes for a quadratic, it always has to be greater than a certain point, so you find the vertex. Now it always depends on the question. Personally, I would probably just look at the range and find the minimum whatever graph you have. In this case, I think the range is, let's see. So the vertex is found at negative 1 over 2. When I plug that in, we get negative 1 over 2 minus 1 over 2. I think it's probably, I think it's y is greater than equal to negative 3. Wait. Can you guys verify that? Yeah. So essentially, when we have a inequality just like so, sometimes you have to write it in terms of set builder notation. Oh, that looks horrible. Sorry. Okay, my bad. So essentially, we have a more proper looking bracket just like so, and then you could say y such that y is greater than or equal to negative 3, and then y belongs to the set of reals, just like so. Oh, are you serious? Oh, so apparently this coordinate is something like 3.125. Okay, so anyways, that is that. So essentially, you would have to keep this in mind when you're writing domain and range. Is sometimes you can write it in this kind of set builder notation. What you can do is you can write it in terms of interval notation. And so what interval notation looks like is something like this. So y belongs to the interval of a square bracket, negative 3.125, and then infinity with a round bracket, just like so. So if you don't already know, square bracket just means like it includes that point. and like a round bracket basically means it doesn't include that point because like you can't go to infinity, right? So I think that's pretty much all for basic polynomial stuff. Now, one thing you'd have to remember is also sometimes certain functions will be even or odd, okay, or neither as well. So what does even or odd mean? I think typically when we learn even and odd, it's like, oh, like 1, 2, 3, 4, 5, right? But when it comes to functions, it's normally easier to look at it when you look at it like a graph, right? So let's say we have the quadratic function, so y equals x squared, just like so. So when you have a quadratic function like this, you basically notice that it's symmetrical about the y-axis. And so what that means is that it has to be even. Okay, so essentially we have for every point f of x, it's equal to f of negative x, right? So for any points on this right side, we can map it to the left side and still the exact same y coordinate, right? And so essentially this is what it means to be even. Now if you have an odd function, okay, what that means is essentially you're reflecting at 180 degrees, or not reflecting, you're kind of like rotating at 180 degrees, and it kind of looks the same. So let's say I have a peculiar function like right here that looks like this. And if I rotate this entire function like 180 degrees, it'll probably look something like this, right? No, I'm wrong. Okay, the more basic function is probably easier to understand. So if you have y equals x, just like so, this is odd because basically if you rotate this 180 degrees right here, it looks the same. And so mathematically, we just define this as f of x equals negative of f of x. Or essentially what you're doing, so essentially what you're doing is you're reflecting it over the y-axis once and reflecting over the x-axis again, and then it kind of still looks the same. So this is what it means to be odd. Okay. This is not correct. This is the same thing. Okay, so and then you also have a neither function. So when you look at a function that's like kind of not symmetric in any way, I'm not wrong. This is not wrong. Okay, so and then if you have a function that's like this, but you can notice it's clearly not symmetric at all, right? It's not symmetric about the x-axis, like you can't really reflect it anyway, and same for the y-axis. So this is neither odd nor even. And so you would basically, in order to verify this, you'd have to make sure that f of x for any like function here, so f of x is not equal to f of negative x, right? So that means it's not even. And you also have to verify that f of x is not equal to the negative of just like this. So you would typically do this algebraically. You would probably sub in like f of x here, and then you just take negative, just like so. Like so, you can think of this kind of like transformations. But yeah, so this is how you do everything kind of algebraically. Cool. And then one last thing we need to talk about is multiplicity. Okay, so essentially we're dealing with a lot of functions, and a lot of them, when we intersect them with the x-axis, they get a x-intercept, and so we call that 0, or we call that a solution to whatever function that is. Now let's say we have some kind of function that looks like this. So it crosses the x-axis right over here. Let's say it has a point of inflection right at the origin, and then it kind of like goes back up, and it kind of just barely touches the x-axis, just like so. So whatever this function may be, what multiplicity means at a certain point just means that like what is the power raised at that specific point, right? So at this specific point, you see how it just goes straight through. This has a multiplicity. This has a multiplicity of 1. Okay. Now at this point, which is the point of inflection, you have a multiplicity of 3, and then so here you have a multiplicity of 2. Okay, so essentially what this means is like when you write this in terms of some kind of function, right? So you take all the roots, just like so, and then like I'm just thinking of them right now. So this is raised to the power of 1, just like before, because that's the multiplicity. Here at x equals 0, it's raised to the power of 3 because it has that kind of like point of inflection, which is where it's like kind of changes curvature, right? And then here we have this kind of quadratic function where it kind of just barely touches the x-axis, so you know it's x minus 5 raised to the power of 2, right? So this is what is meant by multiplicity. Sometimes the diploma might ask you, okay, what is the multiplicity of this factor, or essentially like what is the degree of this polynomial, and so you would have to basically be able to tell the difference. Cool. So we're kind of running a bit low on time for functions, so we might have to push trigonometry a little bit back. We're going to talk about a new type of function now, and I'm sure you all learned it's called which one am I doing? Rational functions. So what rational functions are basically they follow this kind of format. Oh god. Okay. Rational. So rational functions just like so. We have y equals a over x minus h plus k. So if you remember this from what Edward and Jack were talking about earlier with transformations, essentially a is kind of like the vertical stretch. Okay, and then here we have a vertical translation. Here we have a horizontal translation, just like so. And so notice that you don't actually have to do any horizontal stretch. It's not expected. Now, you just have to keep the same things in mind when you're graphing this function. So when you graph this, rational functions probably look something like this. Okay, so essentially we have some kind of horizontal asymptote right here, which just means like it never really approaches that line, right? And then you also have some kind of vertical asymptote, so it never really approaches the x-axis here. And so the way we know the horizontal asymptote and also the vertical asymptote is we try to look and see between the coefficients of whatever is on top and whatever is on bottom, right? So let's say we have a rational function that looks like this. Let's say it's like 2x squared minus 3 over, let's say like 3, and then you have something like 3x squared minus 4, okay? So here the two, essentially like the two leading coefficients, which is 2 and 3, they're attached to this kind of x squared thing. And so essentially you notice that the powers are the same. So essentially for rational functions, you have to remember 3 rules. One is if the degree of the leading coefficient of the numerator is essentially greater than the bottom. So let's say like you have xa over xb, right? So if a is greater than b, right? And you have two coefficients, right? Let's just say there's m and n, okay? So if a is greater than b, essentially you have some kind of slants asymptotes, right? So slants and slant asymptotes do not need to be covered in the diploma, so you do not have to worry about this at all. Now, if you have a equals to b, essentially you have to divide the two coefficients here. So the equation of the horizontal asymptote is y equals m over n. Okay, and then so here you also have a is less than b, which just basically means the y equation is always going to be y equals 0. Okay, so this is kind of three rules you kind of have to remember. And so if on a diploma exam, it's like asking, okay, what is the equation of the horizontal asymptote of this rational function? Here, because these two are equal, we see basically the two exponents here are equal, so we just take the division of 2 over 3. So the horizontal asymptote has the equation y equals 2 over 3, which is this line right here. Okay. Now, in terms of the vertical asymptotes, I believe it always depends on the horizontal translation. Okay, so essentially what that means is for a normal rational function, hold on, I'll just erase everything on the board. So if we have a normal rational function, when we translate it, essentially we're moving the equation of the vertical asymptote, right? And so, okay, no, so for normal rational function, right? Let's say it's 1 over x. The vertical asymptote is at x equals 0, okay? And so when you when you translate this horizontally, so you kind of like move it left to right, what it essentially does is it also kind of moves this equation right here of the vertical asymptotes, okay? So let's just say we have instead y equals and then 1 over like x minus 3, okay? And so what that does is it moves this equation 3 units to the right, and so we have x equals 3, just like so. Or you can just see whenever this denominator portion, so what this thing right here is, when that is equal to 0, okay? So if up here we have x minus 3, we set that equal to 0, and we just algebraically solve for it, x equals 3, just like so, okay? So I think that's more or less all of that for vertical asymptotes and horizontal asymptotes. Yeah, so when you graph a lot of these rational functions, you have to note a few things in mind. So sometimes you have to note down the horizontal asymptote, you have to know the vertical asymptote, and you also need to know the intercepts. So you have to literally physically, I'm pretty sure, write down the intercept of whatever function it is. Sometimes when it like asks you to graph the equation, right? So what that looks like, I'm just going to erase some of this stuff on the board. What that looks like is, let's say you have a graph of this function a over x minus h plus k. So on the xy plane, we have some kind of vertical asymptotes. This is at x equals h. We have some kind of horizontal asymptote, which is at y equals k, like so. And so let's just say a is greater than 0, so we know it probably looks something like this, right? Great. So when it comes to the asymptotes, you can see we have them both here. Now the x and y intercepts, they're probably the two right there. We can solve them with our calculator probably. And then we'd also have to sometimes know the domain and range. Okay. So when it comes to domain, you can see it's defined on every single x you put in, except for whatever is at the vertical asymptote, right? So we can write this in set Euler notation as x, and as long as x is not equal to h, and x belongs to the set of reals, just like so. And then for the range, y, where y is not equal to k for the same reason, and then y belongs to the set of reals. So for a lot of the functions or stuff we've been talking about so far, you might notice that you're kind of always have to know what the domain and range is. Okay, and so I would probably recommend to you, don't try to remember like all the domain and range stuff for every single type of function, but just kind of like know when you see this graph where it's not defined for, let's say, a specific value of x, and the same for y, right? So we know x is not defined for h, so we can't put that there, and same for y. Okay, so in terms of that, that is your domain and range. Now, just one last function. We're going to talk about radicals, and then we're going to move on to trigonometry after that. Do you want to talk about anything? Oh, right. You're so right. There is point of discontinuity. Jack, would you like to do it, or do you want me to do it? All right, so we're going to hand it over to Jack.
谢谢 Alan. Thank you, Edward. Okay. One question, if you remember on the standardizing exam, was very bad for one reason, and that's because the range didn't actually follow this rule. So this is because when you have a function that's in the form of a over x minus h plus k, then it follows it for like every single thing. However, there's like some exceptions where, let's say it's not in the form of this, and the rational function is like fx over gx, where fx and gx are two polynomials. In this case, you have the y-intercept is once again whenever x is equal to 0. The x-intercepts are whenever the top part is equal to 0. And this is because 0 divided by anything is obviously 0. For the domain and for the vertical asymptotes, well, let's start with vertical asymptotes. Vertical asymptotes occur whenever the bottom is 0, whenever gx is 0, and that's because you can't divide by 0, it's going to go to like infinity. And then the horizontal asymptote Alan went over earlier. There's like 3 different ways to get that. One is just like leading coefficients. The other way is sometimes it's just 0. However, what the horizontal asymptote actually is it's kind of the value that y goes to as x goes to infinity or negative infinity. This means that even if the horizontal asymptote is like at a certain level, the graph itself can go past the horizontal asymptote, and that's what happened on our standardizing exam. So let's say, actually I can't think of a function, so I won't do that right now. But what we have to do in order to find the range is we can't simply say it's like not equal to the horizontal asymptote or it's like bigger or smaller than the horizontal asymptote. What we have to do instead is you have to graph it. There's like no other way on the 3D level that you're able to find the range. Sometimes the range is going to be all reals. For example, if you divide by like x squared over x squared, sometimes it looks like something like that. Wait, like that, I think. That happens, some graph like this happens sometimes. And so even though the horizontal asymptote, as you keep on going here, is going to go to 0, we can see that like there's obviously points that are bigger than 0, there's points less than 0. And there's also a point that like goes directly through 0. So that's something to keep in mind. Next part on rationals is also points of PODs, points of discontinuities. I think this is on the diploma, I'm not completely sure. What these are is if there's a common factor between the polynomials on the top and bottom, that means it basically cancels out. However, even though it cancels out, we still have to remember that the domain is restricted. We have to remember that you can't ever divide by 0, and at that point the bottom is going to be 0. So when we have a point of discontinuity, we have like, I don't know, let's say like x plus 1, x minus 2 over like x plus 1, x minus 3. If we were to simply solve this, then you can sometimes just like cancel it out. And so our actual function and what the graph will look like is x minus 2 over x minus 3. But there's going to be a point somewhere along that graph at x equals minus 1, where both the top and bottom is 0, and you can't do 0 divided by 0. So there's going to be like a hole in the graph that's called a point of discontinuity. And that hole in the graph is also going to be the but it's going to be part of like the domain restriction. Point of discontinuities how on the graph though is you just take the value of x that can be there and then you plug it into like the rest of the function. Next thing, we're kind of running low on time, so I'm gonna like really quickly go over the other functions. So the first one is radical function, and this is just square root of something. So square root of a function is always restricted to the function must be bigger than 0. So take the graph of this. If we want square root of x, since you can't take the square root of a negative number, the domain is always going to be here, x bigger than 0, and the range is going to be x, also y is greater than 0. However, there are transformations you can do as before, where you can move this up, down, left, right, and like stretch it or reflect it, and those things will change the domain and range as well. So the general form of a function will be a square root of b times x minus h plus k. And so let's start with this, the original domain and range. The stretches are going to like stretch the range, which doesn't really do anything. What's really important for them is actually the reflection. If a is negative, then it's reflected vertically, and it will look something like that. B is negative, it will be reflected horizontally, it will look something like that. And then if they are both negative, it's reflected both ways, and so it would actually look something like that. And so that obviously changes the domain from like x is bigger than 0 into x is less than 0. After that, the other translations do the same thing to the domain and range. It just moves it up 1, down 1, left or right, based on what the values of h and k are. And so the domain will go from like x is bigger than 0 to, if you move it right, x is bigger than 1. And then next thing is invariant points. So square root, no, I have to do something before that. Next part is the square root of a function. So let's say you have square root of f of x. it follows the same restriction as that f of x must be greater than 0, and so there's no point on the graph of square root of f of x if f of x is less than 0. That is, if it was f of x was like this, then all this stuff over here doesn't matter, it's negative. You only take this part over here to get the square root. After that are invariant points. So square root of 1 is 1, square root of 0 is 0. That means if you have the point of f of x is equal to 1 or 0, it'll stay at that same point, it'll stay at 0 or 1. So on this line here, it would be like this point over here, and then a 1 over here. Those points do not ever change. That's going to be all for square roots. Like I said, we're running low on time. Next one, logs and exponents. So let's begin with logarithmic functions. So what those look like is if we have our axes, like this, right? Let's something like that. This is equal to log of x. Remember one thing, if there's nothing below here, if there's no base, the common base is base 10, and so if you have log of x, that means it's log base 10 to that thing. The other thing I think you probably need to know is ln of x. Ln is natural log, and it just means the base is e, which you can just like take on your calculator. That's the easiest way to do it. So log of this, it has a vertical asymptote here at x equals 0, and then there's no horizontal asymptote. The range is every real number. And then the inside must be kind of similar to a square root. The inside or the input must be positive or bigger than 0. The same transformations of like stretch reflecting, etc. apply here. It can go into like this, or it can like be flipped upside down. Same things. The x-intercept is you have to find for when this is equal to 0, usually at x equals 1. And then though there is no y-intercept because there's like a vertical asymptote over there. Next one is going to be exponential functions. Oops. So the basic exponential function, let's say is like b, I'll just do 2 to the x is going to look like that. So for this one, there is no vertical asymptote, there is a horizontal asymptote at 0, because since 2 is positive, no matter how big or how small x is, it can't ever go negative. So that's why we have a horizontal asymptote over there. So that means the domain is x is all reals, the range is that y is bigger or equal to, not equal to, is bigger than 0. Once again, transformations apply. You can have reflections up and down, and you can translate it like left and right. So what that would look like is just use replacement notation, replace the x with like ax, or like x with negative x. One other thing we have to quickly go over is the use of log laws. All of these are on your formula sheet, but just to like quickly go over them, you have log a plus log b equals log ab. And to kind of conceptualize this, just imagine like it in exponents is like something to the a, something to the b. You multiply them together is something to the a plus b. This works also for subtraction. So if it was a minus, then this would simply be division. And then if you repeat it over and over and over again, then you have a log b. It's just adding b a bunch of times is equal to log of b to the a. Is this it? Oh, and then the last one is change of base. So you have log of a to the b is equal to log b over log a. And then for this new log, you can use any base. It doesn't have to be base 10. You can change it to whatever you want. So on your calculator, you have like two basic buttons. You have a log button and you have a ln button. So you can use either of them to do like the change of base rule. I think that's it, right? Applications. Oh, well, I should know of applications then. Okay, last topic on this, applications of logarithm and exponents. Logarithm, if you remember the graph, it looks something like this. That means over time, it kind of drops down. It doesn't like grow as fast. So logarithm will be usually used for, actually, logarithm is not really used. I don't think it's going to be used on the diploma. What's more important is exponential. Because exponential, there's multiple things you can do. You can either have it grow really quickly, or you can have it fall really quickly. So usually for this one, for the original first case, if it grows really quickly, it's like exponential growth. That's going to be modeled by a times b to the x. And that's just a as a starting value, b as how fast it grows per interval of x. So let's say like something doubles over 7 hours and it starts at 2. So a would be 2, b would be also 2, and then it doubles over 7 hours. So that'd just be x over 7 if x is like number of hours. And then similar thing if you have it as exponential decay, if it like halves every hour or so. Once again, a is the initial value, b if it halves is going to be 1/2, and then x you can like change the divisor on x based on how long it doubles. Oh, why'd you transition it for like 2 seconds? Okay. And then one really quick way that we can use to solve it, let's say you have an initial value, you have a final value. First thing you can do is make an equation, put it in your calculator. Second thing is you can do it as you find out like how many times it doubles. So let's say it starts at like 100 and it goes to like, I don't know, 400. This is pretty easy. You can see that it doubles twice. And then let's say it doubles like once every 7 hours. That means it doubles twice. It doubles every 7 hours. So it means a total time of 2 times 7 of 14 hours. Is that it? Yes. Cool. Time for trigonometry.
Can we hear me? Okay, there we go. Okay, now we're gonna be moving on to trig. One sec. Okay, so in 30 we're introduced first to radians. We're not just going in degrees first, so we're just gonna first go over that. So if we're given an angle like I don't know, 30 degrees, and we want to turn it into radians, we take we multiply by 180 pi over 180 to get your final answer. So this would be pi over 6 in radians. So this is the conversion factor. It would work the same if you have a radian angle. So if I have 2 pi over 3 and I want to get it to degrees, I would use the same conversion factor of 180 over pi to get 120 degrees. Yeah, okay. Now we're gonna go over a unit circle and some types of angles. So in a unit circle is used mainly when to make our lives easier, I guess, for finding a bunch of things in trig. So I don't know how circular this is. I don't know if you can even see that. Okay. All right. So oh my goodness. Okay. So basically, the unit circle is set up as a 360, and then this is 180 degrees. This is 0/360 degrees. I can't read this. This is 90 degrees, and this is 270 degrees. Okay, sounds good. And then those in radians would be 0 or 2 pi here, pi over here, 3 pi over 2 here, and pi over 2 up here. Okay, and then at these quarters, it's 45 degrees here, 135 degrees here. I can do math. 225, right? Okay. And then 350. And then in radians. Radians is 5 pi. 5 pi over 4, 7 pi over 4, 1 pi over 4, and 3 pi over 4. Okay, and then at the Okay, I guess we'll talk about types of angles first. So in each angle, there are 4 types. So you have standard, coterminal, principal, and reference. So standard is basically any angle you're given, basically from the question. Coterminal is if, for say, I have I don't know, 116 degrees. Coterminal would be the same angle, but it's plus or minus 360 degrees. So because 116 is in this quadrant right here, it is in the same quadrant. It is the exact same angle. It's just plus or minus 360. So it's going to look the same no matter what. So a coterminal angle to 116 would be 476 degrees. Same thing would go for 116 degrees minus 360, which would be thank you, 244 degrees, negative 244 degrees. Okay, and then for reference angles, so reference angles are the angles that are closest to the x-axis. So if you were in quadrant 2, it would be this way, so it would be this way. Quadrant 3, it would be this way. Quadrant 4 would be this way, and quadrant 1 would be this way. Basically like that all the way around. And then the last one is principal angles. So principal angles can be anywhere from 0 to 360 degrees, basically. Okay, so starting off with this side then, this would be 30 degrees or pi over 6. And that would be the same as over here because this is the reference angle for this is 30 degrees. So it'd be 150 degrees or 5 pi over 6. Same with your reference angle, so 7 pi over 6 or 210. And then same over here with 330 or 11 pi over 6. An easy way to remember this is all of the 30 angles with reference of 30 have a denominator of 6. And then 60 degrees up here or pi over 3, 120 here or 2 pi over 3, 240 over here or 4 pi over 3, and then 300 over here or 5 pi over 3. So same pattern with these to memorize is the reference angle for all of these 60 degrees, and they all have a denominator of 3. Okay, cast rule. So the cast rule goes like this. Basically, it's an easy way to use if you are given the value of like a cos angle something and you're trying to find that angle, and so like cos theta is equal to 2.14, I don't know, sorry, not 2.14, 0.14. Because you know this is a positive value, cast starts in the 4th quadrant, by the way. Because you know this is positive value, you know it's either going to be in quadrant 4 or quadrant 1, because cast is I don't know if they can see me. Cast is basically these angles are where the positive values for that are. So cos is positive here, sine is positive here, tan is positive here, and all of the cos, sine, and tan are all positive here. Okay. Sine, cos, tan. Sorry. And then, okay, the unit circle with sine and cosine. So the unit circle basically uses the rule that the radius is equal to 1. So with that in mind, we'll start with the 45 degrees. So if the radius is 1, and using Pythagoras' theorem, which is a squared plus b squared equals c squared, if we know that c, which is this, is equal to 1, then we know that c squared is equal to 1. So a squared plus b squared is equal to 1. So you get, oh my goodness. Oh my goodness. I'm having a brain fart. I'm having a brain fart.
Sine x squared plus cos x squared.
Huh?
Sine x squared plus cos x squared equals 1.
No, I'm trying to find A and B. I'm trying to find A and B. Sorry, the square root of 1 over 2. Right? A and B are both equal to...
Yes.
Okay, yeah. Okay, sorry. So, the x and y for 45 degrees are both, so the coordinate point for it would be 1 over root 2, 1 over root 2, which if you rationalize would be root 2 over 2, root 2 over 2. And that applies for all of the 45 degrees, but you have to consider the fact they're also in the quadrant, so there will be negatives. So this would be negative root 2 over 2, negative root 2 over 2. This one would be negative root 2 over 2, 2 root 2 over 2. And then this would be root 2 over 2, negative root 2 over 2. Okay, and then next we'll do the 30 degrees and the 60 degrees, which are kind of the same triangle, just in if you look at it a different way. What? Oh, right. Okay, sorry. So this is the isosceles triangle of 45 degrees. So this is 1, this is root 2 over 2. This is for the 30 degrees. So there's a rule in the 30-degree triangle that the hypotenuse, which is 1, because it's the same, you move it down here, it's this, it's the radius, which is 1. There's a rule that the side that is opposite, the hypotenuse is double of the angle that the 30 is facing, if that makes sense. So basically, because the hypotenuse is 1, the angle that the side that faces the angle 30 is 1/2 of 1, so 1/2. So then the side that faces the angle 60 will be sorry, root 3 over 2, just by Pythagoras again. So if you put that into the points here, you'll get sorry, this is the angle 30. So you will get 1/2. This the y is 1/2, so this will be root 3 over 2, 1/2, 1/2 root 3 over 2. And then the same thing will follow for all of the things, but considering the fact that the x will have to be negative here, both of them will have to be negative here, and the y will have to be negative over there. Okay. Hold on. There's also a thing where the coordinate point here will be cos that theta and tan, sorry, not tan, sine the theta of the angle. So you can use that too to find it. Constructing triangles, Trig ratios, equation of a circle. Okay. Is that good? Is that good? Okay. I guess for the reciprocals that they're talking about is we have cosecant, secant, and cotangent. So they're way of space. They're represented as CSC, SEC, and COT. So this is cotangent. This is secant, and this is cosecant. And basically, this is 1 over sine. This is the reciprocal of sine. This is the reciprocal of cos, and this is the reciprocal of tan. Okay. Now we're going to talk about the arcs and sectors, I guess. Okay. Want to take a picture? Okay, sounds good. Oh wait, I forgot 90 and 180. Hold on. Okay, sorry. So there are also the points just for 90, 180, 270, and 0 or 360. This is 0, 1. This is -1, 0. This is 0, -1, and this is 1, 0. So yeah. Okay. Yippee. You're also given a piece of scrap paper on the diploma. So if you want, like, straight out, just to have this, a lot of people do, just write it down immediately, just straight from your memory, basically. It should help a lot during the test. Okay. Okay, sounds good. So we're gonna take a quick 5-minute break. We just have to move rooms really fast, but we will be right back.
Hi guys. Okay, so basically we're gonna be back at 2 p.m. So we're gonna have like a quick 5-minute break. Cool.
No, you are not. Hello? Okay, we're back. Can everyone
Wait,
hear me?
Wait, hold on.
Can anyone hear me? I don't know if anyone's
It's
there.
on the we'll be right back screen, right?
No, it's transitioning back.
Okay. Quick transition.
No, we are
Wait, what? What?
Okay. Okay, perfect. We're good. Heard. Fantastic. Thank you, Olivia. Okay, so we're gonna continue. So now we're gonna do arcs and sectors. Okay. We've moved to, I'm sorry. If anyone can't see anything, please let us know because we have a smaller board. So okay. Arcs and sectors. So a lot of times on the diploma, they're going to give you a question where it's like an application sort of question, and you're going to basically have to calculate the length of an arc. So you're going to be given an angle. So for example, let's say there's a windshield. Windshields look like this, and this is an angle of 135 degrees. So and the radius is of the entire thing is 15 meters, and I want to find the arc length of this. So arc length is calculated through theta times r. So theta, but theta has to be in radians. So I will first convert 135 degrees into radians, which would be like that, and then I times it by the radius of 15 meters. So I would get an answer of 45 over pi meters. Basically, it's just a much faster way, because the classic way that a lot of people might do it is they would take the circumference of the entire circle, and then they take the 135 portion. So you take pi d times 135 over 360, which you can do still, but this is just a much faster way that has proven to work. Okay, and then arc sectors. So the area now for arc sectors. So the area is calculated using the formula Is this the formula? Edward, this is the formula?
Yes.
Okay, fantastic. Sorry, the area is calculated using theta r squared over 2. So it's the same thing, basically. You take the one, if I'm trying to find this area that the windshield covers, I would take 3 pi over 4, because the theta still has to be in radians. I'd multiply it by 15 squared, and I divide it by 2. So I would get 3 pi over 4 times 225 over 2. And 675 pi over 8, I think. If my math is wrong, please tell me. Okay. Oh my god. Okay, so yeah, and that would also be in meters squared. Don't forget units. Okay. Now we're going to be moving on to functions of sine and cos graphs. So, okay. I can do it for a bit, yeah. Okay, so sine and cos graphs. So the basic function of both sine and cos graphs is sine starts at the origin, and cos starts at one of the amplitudes, like that. So this would be sine. This would be cos. So the functions of a wave graph there is the amplitude, there's the there's the period, there's the horizontal displacement. Sorry, horizontal phase shift and vertical displacement. So they're like the four main things. It still follows like the same y equals a bx minus h formula plus k formula. It's just each one of these corresponds to one of those. So A is amplitude, B is period, but there's another calculation you have to do. H is horizontal phase shift, and K is vertical displacement. So let's start with amp and period first. So amplitude is basically when you find the midline of a function and how many it is away at the most, so the max and the min. So for example, this could be, if this is at 5 and this is at -5, the amplitude is equal to 5. The period is from basically when the wave repeats itself. So when it hits the same point along that midline, how far has it crossed the x? So in a cos and a sine function, the calculation is b over 180 over b. 180 over b? 2 pi or 180 over, sorry, 2, yeah, sorry.
360.
Yeah, 360. 360. 360 over b or 2 pi over b. And so this is for cos and sine. And then in a tan function, it's 180 over b or pi over b. Okay. And then when you add the horizontal phase shift and the vertical displacement is where things start to get a little bit more complicated, because you could have potentially more than one answer. So the vertical displacement is the midline. So in these examples, both of them, the midline is 0, but you could have a function that is like this, where the midline is not at 0. This could be y is equal to 3. So the midline then would be, the k value would be at 3. And then the horizontal phase shift, we'll continue with this example. So the points where it hits the midline again is here and here. So let's say the period is, let's say this distance that it's traveled is 3 pi. So then the b value would be 2 pi over 3, otherwise known as 2/3. So you start from there. You'd start with the period, and then you'd work back to the horizontal phase shift, because you could have two potential values for the phase shift, one that's positive and one that's negative. So if we have this, we can see that to get it back to where, let's use cos. Let's use sine. So if we want to get it back to the where x is equal to 0, we can either go this way or we can go this way, which is how you get your two different answers. Good? Okay. Sine or cos, depending on. Do you want to do tan? You want to do tan? Okay, sounds good. All right, we're gonna head now back to Edwards to do tan. Did I forget something?
So tangent doesn't have like that kind of.
Oh yeah. Okay, do you want to do reciprocals and inverses? Yeah. Okay,
I'll go try.
okay, sounds good.
Okay,
Okay, sounds good. All right. We're now going to move on to Edward, who's going to teach us about tangents. Oh yeah. Hold on. Take these first.
sorry. So we're gonna have a quick 1-minute break just to switch some microphone stuff going on, and so yeah, we'll see you back in 1 minute.
Woohoo. Okay. So before. Okay. So Marley just did sine and cosine, and now we'll talk about the amplitude, the domain, range, period, and intercepts of tangent of theta. So a tangent graph looks something like this. And the idea is that there are vertical asymptotes that occur periodically that restrict the domain of the function. So y equals tangent of theta. As some of you might know, tangent theta is also equal to sine theta over cosine theta, correct? So the points at which tan theta is undefined, aka these vertical asymptotes, is a point at which cosine theta is equal to 0. And I'm sure this is very easy to do for a lot of you, so I'll just give you the answer. The answer is that cosine theta is equal to 0 at pi over 2 plus pi k, where k is an integer. Or more formally, we can also write this as pi over 2 plus pi k, comma, k is in the set of integers. So now for the range of tan theta. The range of tan theta is actually very, very straightforward. Because the idea is that in each of these mini sections of tan theta, it goes all the way from negative infinity to positive infinity. So the domain of tan theta is actually just y is in reals. Period, right. Next thing we need to discuss about the graph of tan theta is its period. So the period of the original tan theta graph, y equals tan theta, is just simply 180 degrees or pi in radians. So as we've discussed before, if you have a scalar in the middle, for example, y equals tan of b theta, this will change the period. And how much will it change the period by? Well, the new period will be 180 degrees divided by b, or pi divided by b radians. Is there anything else we need to do for tan? Range. Range, as we've discussed, is all reals. Domain is x cannot be these things. But I think in the diploma, they will not ask you to write the actual range. They'll just ask you, like, what are the points at which this function is undefined, and then you can just write this. So now we're going to move on to an application. Oh, yeah, it's okay. So actually, Jack just brought up a good point. They might also test you on the intercepts of the tan theta graph. I'll just draw on these arrows to make it more accurate. So this is also pretty straightforward because y equals tan theta equals sine theta over cosine theta. And because of that, the intercepts, the x-intercept, will occur at any point at which sine theta is equal to 0. So when does this occur? Well, sine theta equals 0 at pi k, where k is in the set of integers. And I believe that's it. Yeah. Sorry? Oh, that was already covered. It's fine. It's fine. So, sorry. Actually, there's one more thing I should probably discuss, is that the points at which the x-intercepts occur will be changed if you have a scalar in the middle as well, or if there's any transformations that modify the function. So for tan b theta, all you have to do when you get a tangent graph is just convert it into sine over cosine. And that way, you can just see whenever sine b theta is equal to 0 to find the x-intercepts, because it's in the numerator. And then you can check whenever cosine b theta is equal to 0 in order to find the points, what is it called? Domain discontinuities? No, vertical asymptotes, sorry. Vertical asymptotes. I think that the key thing to remember for any tangent graph is to just remember it can be expressed as sine over cosine. And in that way, a lot of tangent problems can just be reduced to this, which is easier to solve for. So next thing we'll go over is a quick application of trigonometry to real-world problems. Woohoo! So the problem is you're riding a Ferris wheel with a diameter of 40 feet. So if the diameter is 40 feet, then obviously the radius will be 20 feet. Right. When the last seat is filled and the ride begins, your seat is at approximately 4 o'clock. So basically what it means by this is you have a clock, right? Is this 4? Okay, wait, sorry guys. I haven't read a clock in so long. When the last seat is filled, and okay, so your seat. This is your seat at the beginning. So it takes 3 seconds for you to reach the top, which is 43 feet above the ground. 43 feet. So because the diameter of the Ferris wheel is 40 feet, actually what this means is that the Ferris wheel is 3 feet above the ground. It takes 3 seconds for you. So it takes 3 seconds for you to reach the top. 3 seconds to reach the top. And the wheel makes 1 revolution every 8 seconds. 1 revolution, aka just 2 pi radians, every 8 seconds. So now the question here is to write the equation of your height above the ground as a function of time. So we know that f of t, first of all, has to represent the height. This is the height. This is the height. And then t is the time elapsed. So first of all, we can just express this as a sine or cosine function. I'll choose sine, but the thing to remember is that sine and cosine are essentially the same up to translation. So a sine bx minus c plus d. These are just placeholder values for now. So the first thing we need to do is to find the amplitude. Because the Ferris wheel has a diameter of 40 feet and a radius of 20 feet, it'll oscillate between this and, how do I say it? It'll oscillate between the lowest point and the highest point. And the amplitude of a function is simply equal to the maximum minus the minimum divided by 2. So the max minus min, that's just 40 feet over 2. And that would mean that the amplitude is 20 feet. For the sake of our function, we'll just assume that the height is expressed in feet, and we'll just write a equals 20. A equals 20. So now, what about b? So we're actually given the information that it makes 2 pi radians, or 1 revolution, every 8 seconds. So if it makes 1 revolution, or 2 pi radians every 8 seconds, that would mean that the period is let me see how. 8 seconds. It's okay. Period is 8 seconds. Sorry, guys. 2 pi over b. Oh, yeah. Sorry, guys. So the period is 2 pi over 8, which is equal to pi over 4. And this is simply because we're rotating 2 pi radians every 8 seconds. So to get the period, that's what we just... Oh, no, yeah. Wait, sorry. Okay. The period itself is just the amount of time it takes to rotate through 2 pi radians. So the period is simply 2 pi, 8 seconds. And the period can also be expressed as 2 pi over b equals 2 pi over b, where b is this value. And eventually, what we do is we solve for b, which simply gets us b equals pi over 4. b equals pi over 4. So now, before we do c, we'll just quickly do d. So d is simply the midline of our function, or kind of like the average. So eventually, what we do is we take the maximum, we add it to the minimum. So the max would be up here, the minimum would be here. The maximum is 43 feet above the ground. So this over 2 equals 43. The minimum is only 3 feet above the ground because that's what the lowest point is. Plus 3 over 2 equals 26. So if our midline is at 26 feet, that will simply represent our d. D value is 26. And now finally for the value of c, or kind of like the horizontal phase shift. So the idea here is to just take your equation here. Let's see. Let me see how to do this. Read. So you're going to take the initial time. This is the initial time. And then you're going to find its height. So the initial time is at 4 o'clock. And each hour of our hand of the clock is like 360 degrees over 12, which is 30 degrees. So this would simply be, because there's 2 hours here, 60 degrees. So then by the unit circle, we have that. So this is 20 feet. Unit circle says that this is half of that. So this is actually 10 feet. Oh, sorry, D is 23 because you're dividing 46 by 2. I don't know why I said 26. So now this total height is equal to 20 plus 3 is 23 feet. So actually your seat at the very, very start is just 23 minus 10, which is 13. So plugging that in, we get 13 equals A is 20, 20 sine, B is pi over 4, pi over 4, and x minus c. X is 0 because the time is 0. And then we just add our value of 23. And what ends up happening is we can just solve for this value of c. So 13 equals 20 sine pi over 4 times 0 minus c. That's just negative pi over 4 c plus 23. Subtracting gives us 23 minus 13 is negative 10 over 20 equals sine negative pi over 4c. And this is just simply negative a half equals sine negative pi over 4c. So negative 1/2. So when is sine equal to negative 1/2? That's at 210 degrees. 210 degrees, or that would also be 7 pi over 12 radians. Equals sine of negative pi over 4c. And then what you do is you simply divide to get 7 pi over 12. Sine is, pi over 7 pi over 6. Oh yeah, you're right. 7 pi over 6 equals this. Multiply both sides by 4, divide by negative pi. Eventually what you get is 14 over 3 pi. Oh no, there's no pi. Negative 14 over 3 equals c. And eventually you just substitute that in to get c equals this. And our final equation is just f of t equals 20 sine b is pi over 4 x minus negative 14 over 3, so that's just plus. And then plus d is 23. This is, t. Oh yeah, you're right. This should be t because the parameter you're taking in for the original equation is time. So you have to use time as a variable in the equation. So that's basically how you solve this problem. So as a recap, whenever you're tasked to find a equation for a certain situation, what you want to do is first of all write out the equation for the general equation for a sine graph. Next, what you want to do is you want to take each of these points, each of these 4 parameters, A, B, C, and D, and you want to find each of them. So A is the amplitude. B is the horizontal phase shift. Horizontal is horizontal. You can say it's a horizontal stretch, but it's also equal to 2 pi over the period. And C is equal to the phase shift, which you should always find last. And then there's D. D is simply the midline, or also the vertical displacement. So amplitude can be found with max minus the minimum divided by 2, which, as Marley has said before, is the distance from the midline to one of the crests. So it'd be like this. C, the midline, can be found by kind of a similar formula, but instead of minus, you would use plus. It's the average, yes. So, maximum plus minimum over 2, and that just simply represents the y coordinate of the kind of like the middle or average of the graph. And then the last step is obviously to just take all these values, substitute it back into your equation, and then you'll be left with an equation that models your situation. Plug and profit. Identities. Okay, I'll do identities. Let me see what we have to cover next. Solving equations. Okay. Yeah. Okay. So we'll just quickly go over solving equations. So basically, usually when you have a sine equation, like 2 sine theta equals square root 2, where there's only one trigonometric function, you're just going to move all the constants to the other side, and then you're just going to take sine -1 of both sides. Just reverse the sine -1 of root 2 over 2 to find the possible equation, the possible values. But also you have to be careful of not just this value, but also values that are not equal to this but can also produce the same value for sine. For example, if we have like sine theta equals square root 2 over 2, if we draw out the unit circle, we can easily see that it occurs at 45 degrees. But also, sine theta equals square root 2 over 2 can also occur here because it is the same height. So you have to be aware of all these different solutions to the equation when you're solving. And so if you want to get the general solution to any of these trigonometric equations, all you have to do, if it's just like sine theta, is to just add 2 pi. So if you get theta equals 45, or equivalently pi over 4, all you have to do is to just add 360k or 2 pi k where k is just an integer. So the way you would write this is theta equals 45 degrees plus 2 pi k, the comma, and then k is in the set of integers. Usually the best way to do this is to just find all of the equations in the range of 0 to 360, and then you just want to add 2 pi k to all of them. So theta can also be equal to, in this case, 135. Oh, wait. Sorry. Pi over 4, 3 pi over 4, plus 2 pi k, and k easy. Yeah, so those are the general solutions. So now let's move on to a more nuanced example. So actually, to solve these more complicated trigonometric equations, we're going to need the help of some identities. So obviously, we have sine squared theta plus cosine squared theta is equal to 1. Oh, yeah. That's our Pythagorean theorem. And then we also have our sum identities. So if we have alpha plus beta, this is just simply equal to sine alpha cos beta plus cos alpha sine beta. And then if we have cosine, that is just cosine alpha cosine beta minus sine alpha sine beta. So actually, for both of these trigonometric identities, we have a special case where alpha is equal to beta. And in that case, we get the double angle identity. So the double angle identity is simply when we have sine of 2 alpha. Notice this is just alpha plus alpha. And if we use the sum identity on the top to calculate this, we get that this is equal to 2 sine alpha cosine alpha. Similarly, for cosine, we get cosine 2 alpha equals cosine cosine squared alpha minus sine squared alpha. And actually, this one also has two alternative forms by using the Pythagorean theorem to change all of the cosine or sine into sines. So if you change it all into sines, you get 1 minus 2 sine squared alpha. That's simply by plugging in cosine squared alpha equals 1 minus sine squared alpha. And then this is also equal to 2 cosine squared alpha minus 1. Are there any other identities we have to go over? Oh, right. Difference identities. You could memorize them, but I don't think it's that helpful because essentially what you're doing is you're just doing sine alpha plus beta, but you have beta negative. So you can just express this as sine alpha plus negative beta, which can be evaluated with our sum identity up here. So the last identity we have to go over is tan. So first of all, the proof of this is quite long, so I'm not going to go over it. But if you have the sum of two angles in tangent, essentially what happens is this is just equal to tan alpha plus tan beta over 1 minus tan alpha tan beta. So now we're going to use these trigonometric identities to help solve a problem. This one. Okay. So we're going to first equation we're going to solve is, so we have here 2 sine squared x plus cosine x is equal to 1. So the first step in any trigonometric equation is to just look out for any impermissible values. In this case, there are none because sine x and cosine x all have a domain of x's and reals. So no restrictions in this case. So we can proceed by using our identities. So notice we have a sine squared here and a sine squared x, and then we have a cosine x here. But to solve this equation, we actually need to convert all of the sines into cosines. So one way we can do that is by using the Pythagorean identity. The identity says that sine squared x plus cosine squared x is equal to 1. And equivalently, sine squared x is equal to 1 minus cosine squared x. By substituting this into the equation, we get 2 times 1 minus cosine squared x plus cosine x equals 1. And 2 minus 2 cosine squared x plus cosine x equals 1. 2 minus, so we're just going to subtract this to move everything to one side. Negative 2 cosine squared x plus cosine x plus 1, plus 1 equals 0. So first, what I'm going to do is I'm just going to multiply everything by negative 1 because I don't like this negative leading coefficient here. It doesn't change the solutions because negative 1 times 0 is just 0. So 2 cosine squared x minus cosine x minus 1 equals 0. And notice what we have here is a quadratic equation in cosine x. So we can simply factor this. 2 cosine x. Let me see how this factors. Cosine x minus 1. Be a minus 1 here and a plus 1 here. Equals 0. So in this case, we could either have this equal to 0, or we could have this equal to 0. Let's start with this one because it looks a lot simpler. This just evaluates to cosine of x is equal to 1. So when is cosine x equal to 1? Well, what we're going to do is we're going to draw out the unit circle. Cosine x equals 1. That just means that the x coordinate is equal to 1. So this is the only point. The only point is here on the unit circle, where cosine x would equal to 1. So we just have 0 degrees or 0 radians, where this holds true. But obviously, we also have points where you can get the same value, but it's like plus 2 pi. So 0 plus 360k would generate the general solution to this equation. And then we have 0 radians plus 2 pi k, or just simply 2 pi k. We can take out the 0 because it doesn't mean anything. So 2 pi k, where k is in the integers, would be the solution to this equation. Now, our second case is where 2 cosine x plus 1 is equal to 0, and cosine x is equal to negative a half. Using our unit circle again, when cosine x is equal to negative 1/2, we have this angle right here, negative 1/2. This angle is simply 120 degrees, or just 2 pi over 3. And then this one is 4 pi over 3. These would both have a value of negative 1/2. But to generate the general solution, we would also need to add 2 pi k. So we have 2 pi over 3 plus 2 pi k. K is in. And then we also have 4 pi over 3 plus 2 pi k. K is in integers. So by grouping all of these together, we would get all of the general solutions to this equation. And that's how you solve it. So as a recap, first you're going to check for restrictions. Check for restrictions. Second step, you're going to start using your identities to reduce it to a more manageable form. Reduce. And then the last step is to just compile everything together, get all of the solutions, and then add 2 pi k. Get solutions and account for general solution by adding 2 pi k. Yeah. Oh, so the idea is that you can also verify your solution to the equation on your calculator. This is supposed to be 2 sine squared x. Yep, 2 sine squared x plus cosine x. Two sine squared x plus cosine x minus 1 equals 0. So essentially what I'm graphing here is the equation in a slightly modified form. I've subtracted 1 so that I can use x-intercepts to find the solutions. So I've graphed out the equation, and now by using calc, 0. This is for a TI, by the way. Yeah. You can check each of the solutions and see if it aligns with what you've solved for here. And eventually, if everything checks out, then you have the right answer and you can move on to the next question.
Hello, hello, hello. Are we working? Okay. Sorry, our microphone died. We're back. Hello. Okay, sounds good. Okay, we're gonna do some proofs of identities. So, okay, jeez. Okay. Okay, so basically the basics of proofs for identities is you use the formulas that are given to you on the formula sheet to try to prove that both sides are equal to each other. So you can do this three ways, I think. So one way is you can take the left side and brute force it into the right side. You can take the right side and brute force it into the left side, or you can do a little bit of both where you just make them eventually equal to each other. So we're going to take this example here. Tan x over cosecant of x is equal to, sine squared x over cos x. So a way that you can organize your work, if you want to, is in a T-chart, if you want to. So just like that. So what I'm going to do is I'm going to start with the left side. So tangent is sine over cos. Okay. Sine over cos x times, this is divided by 1 over sine x, which then you can take sine x over cos x times, you reciprocate this as sine x, which would then just get you your answer of sine squared x over cos x, which is equal to that. Okay, so that's just an easier example. You want to do another one? Restrictions. Okay. Restrictions. So basically how restrictions work is in a fraction, you cannot have the denominator equal to 0. This is undefined, therefore it doesn't work. So for these ones, you basically account for both of them if they were 0 as your restriction. So cosecant x cannot equal 0, and cosine of x cannot equal 0. So let's start with the cosine one. So if cosine x is equal to 0, then x is equal to, by the unit circle, it would be equal to 90 up here or 270 down here. So cos x cannot be equal to, if you want to write it in general form, n pi over 2, where n is any real number. And then for cosecant x cannot equal 0. This is cosecant is also 1 over sine x cannot equal 0, which okay, so am I doing something wrong? Okay, good. Okay, you're scaring me. Yeah, well, 1 over something can never be 0, so this just is any answer. So there you go. Okay. Are we moving on now to terms? Or what is next? Okay, fantastic. So now we're going to move on to perms and cons. I'll start with the basics, like counting principle. Okay. All right, Jack's going to move on with perms and cons.
Great, Jack.
Here. Okay.
Hello, everyone. So to begin with permutations and combinations, I think we should first start with counting principles. So what is this? Let's say you have like, I don't know, let's say you're making an outfit. You have like 3 hats, you have like 5 shirts, you have like, I don't know, 7 shoes. So the way we learned it before is you make a big tree diagram. You start with the 3 hats, and each of these can branch out into 5, and then so on and so forth. However, this is very tedious to do, and we don't want to waste our time, even though we have 6 hours on the diploma, doing something like this. Okay, so what we want to do instead is we want to like simplify this to count the number of ways in an easier manner. When we look at this tree diagram then, in the first step, there's like 3 possibilities. In the next one, each of those 3 possibilities branch out to 5 more, and then each of those ones branch out to 7 more. So if we want to count the total number of possibilities, all we have to do is take the options and then multiply them by each other. So 3 times 5 times 7, and this is equal to 105. And obviously, if there's 105 different combinations, you don't want to be like drawing out a big tree diagram and listing out every single one. So now that we have this in mind, let's talk about what happens when we want to, like, say, order a word. So let's say a word has 7 letters of just, let's just do friends. Okay, so we want to rearrange this in some manner. So there's 7 slots for letters to go into. And using the counting principle from earlier, in the first one, there's 7 possibilities. It can be any of the letters. In the next one, it can't be the first letter. There are 6. And the one after that, it can be any of the first 2 letters. So there are 5. And then if we go on to the end, it's 7 times 6 times 5 times 4 times 3 times 1. 2 times 1. Sorry. However, this is also pretty tedious to write out. So that's why we have a shorter form of doing it, which is represented by the exclamation mark or a factorial. So that's what the definition of factorial is. It's basically the number of ways you can order a certain number of things. So in this case, 7 letters, there are 7 factorial ways to order it, and that's just 7 times 6 times 5 all the way to times 1. So for the definition, n factorial equals n times n minus 1 times so on times 2 times 1. So that's what factorial is. After we have factorial, there's 2 additional steps, 2 other ways to, like, count arrangements. So let's say we have the same 7 letters. However, we don't want to use all 7 of them. We only want to use, let's say, 3 of them. So same thing as before. In the first slot, there's 7 spots available. In the second one, there's 6. In the third one, there's 5. And so all we do is 7 times 6 times 5. So where does factorial play into this then? Is that it still is 7 factorial. It's just that we only take the 3. So everything after this, so 4 and so on, we don't need it. So we can divide by the 4 factorial after that. So 7 factorial divided by 4 factorial. This is the same as 7 pit 3. Otherwise known as just like multiplying the first 3 parts of the factorial, 7, 6, and 5. For the definition of pit or permute then, we have n p k is equal to n factorial over n minus k factorial. And all this is taking like only the first k numbers of n that you like multiply together. Now the additional layer on top of this pit is called choose. And so what choose is let's say we have 7 letters again, but we don't care about what's first, we don't care about what's second, we don't care about what's third, the order doesn't matter. So there's still 7 letters, so we can start with 7 factorial. We don't care about the last 4 since we only want 3 letters, so we divide by the 4 factorial. And so now we have 3 letters that are in a specific order. So what next then? We want to find the number of ways in which we can order these 3. So from before, as you know, the number of ways to order 3 things is simply 3 factorial. And so since there are 3 factorial ways to order these 3 things, we divide by that number 3 factorial. So what this does is it takes like the 7 letters. First slot there's 7, second slot there's 6, third slot there's 5. That's why we divide by 4 factorial 4. Now we have the 3 letters chosen. How many ways can we order them? Because we don't want them in the specific order, so we divide by the 3 factorial. So that's what choose is. And so if we want to define n choose t, we have n factorial over n minus k factorial over k factorial. One pretty quick way to do this in your head is just like the way I did it just now. Let's say you have n choose 3. You take the first 3 numbers from it, so 7, 6, 5, and then divide by 3 factorial, which is pretty easy to calculate as 6. So those are the basic ones of factorial, pit, and choose. So the next part is, when do you use which one? Factorial you use whenever you want to use every single item in like a group of things, and you want to find the number of ways to order that group. For pit, it's the number of ways to order only a certain number. So like before, if there are 7 things and you only want to pit 3 of them in a certain order, it's 7 pit 3. And then lastly, in choose, it means that the order doesn't matter. All you're doing is you're choosing 3 objects to form a group. And the group can be in whatever order. It's all counted as the same group. Next part is, what if there's repetition? What if, say, there are like, let's say you want to like make a bracelet or something, and there are like 3 red beads and 2 black beads and a bunch of other different colored ones. So in that case, let's consider it as A, B, B, C, D, or something like that. Let's start with factorial. Let's start with we want to order all of them. Actually, that's the only way. Let's just say we want to order all of them. That would be 5 factorial ways, because there's 5 letters. However, because there's repetition, those letters can be thought of as the same, and so they can like switch around and still be counted as the same thing. So because there's 2 letters though, we want to divide by 2. Let's add in another B. What happens now? Now there are 6 objects, so you do 6 factorial. And now there's 3 of them, and those 3 can be swapped around in any order. So you don't just divide by 3, you have to divide by 3 factorial. And so that's how you do it. If there's repetitions, you take all of them, factorial it, and then divide by the repetitions factorial. So if I had another C in here, the B's can switch, but then so can the C's. So you have to divide by the 3 factorial and also the 2 for the C. Okay. So another very common problem is when it gives you a certain number of letters and it gives you another restriction on top of that. So what I mean by this is you have like a word to order, but the first letter has to be a vowel, or maybe 2 letters have to be together. Let's take those 2 cases separately. So let us consider that we have like ABB. Let's just do A, B, B, C, D again. First letter has to be a vowel. If the first letter has to be a vowel, then in our 5 slots, one of them is already decided. It's the A. The other 4 now can be the order of the rest of these, which by what we just learned is 4 factorial divided by 2 factorial. So let's say we have another restriction. The first letter is a vowel, the last letter is a D. So we first set the ones that we already know are true, so the A, and then D at the last one. And now there's 3 spots left for the 3 remaining letters, and we do once again 3 factorial divided by 2 factorial. So when you're given something that's already set, you want to make that thing like happen first and then do what you can with the remainders. Next part. Let's say a certain group of things has to be together. So let's consider A, B, C, D, E. And in this one, A, B have to be beside each other. So what we can do is we can kind of slot this out into like chunks. So first is the AB chunk, and then we have a C, a D, and a E. There are 4 chunks or like sections here. So we do 4 factorial for the number of ways to order those like groups. And then in this one group with an A and a B, that group can be ordered in 2 ways for AB or BA. So we multiply it by 2 factorial. You do the same thing repeated if there are larger groups or if there are more groups. First divide it into how many like sections there are in the word, and then multiply by how many ways can you order each section. Okay, next one on another thing that is kind of useful is the complement. So what the complement is you're trying to find what something cannot be and then subtract it from the total. So what does this mean? Let's say you have a group of like, you want to make a group of 5. There's like 7 A's and 2 B's. And you want to find the number of ways so that there is at least 1 B wait, this doesn't work out. Okay, let's do like 7 teachers and 2 students, or 7 students and 2 teachers. You want to make a group of 5. So how many ways are there so that there is at least 1 teacher? So it's kind of hard to do if you want to do 1 teacher and then 2 teachers, because that's more calculations. Instead, what you can do is find the total number of ways to make 5. So that's just 10 choose, 9 choose 5. That's the total number of ways. And then you want to subtract all the ones where there is not at least 1 teacher, or where there is 5 students. So that would be simply 7 choose 5. And that's what the complement is the 7 choose 5. The number of ways, so if you want to find if there's at least 1 teacher, you find the opposite if there are no teachers. And then you subtract it from the total. Because everything else from the total means that there will be at least 1 teacher, because you like already subtracted the cases where there are less than 1. Want to do it? Or I'll do pathway. Yeah. Okay. So I'll start off with applications now, which Alan will be able to finish. So the first thing that's pretty important is pathway problems, or how many ways can you go from one place to the other? So let's say you start on the bottom left corner, and then you can only go right and up, and you want to end up at the top right corner. So how many ways are there to do? How many ways can you do this? So to start off, we can go. Okay, so there's 2 ways to do this. The first way is something called recursion, or you just want to add the number of ways to get to somewhere from, like, I don't know, from before, and you'll see what I mean in a minute. So from here, there's 1 way to get here, 1 way to get here. If we take this point now, we can get there in 2 ways, from here, from the bottom and from the left. So there's 2, and then if we keep on adding it down, so there's 2 here, and there's 3, 4, and then 5, and similarly 3, 4, 5. Over here, we add up the 2 3s to get 6, and we add these to get 10, and then 15. 6, 10, 15. And then we add the 10s to get 20, the 15 and the 20 to get 35, and the 15 and the 20 to get 35 again. Now that means if we do this like until the very last point, we add the 1 from the left and from the bottom, we get that there are a total of 70 ways to do this. There's another method of solving these problems, which uses the choose and pick that we just learned earlier. So let's take the same pathway again. In total, we must make 4 moves to the right, and we must make 4 moves upwards. That means a sequence of moves, or a unique path, or a way of getting there, can be modeled as 4 rights and 4 ups. And we want to find a way to order these 4 rights and 4 ups. How do we do this? Well, there's 8 total things, so we do 8 factorial. And then there's 4 rights, or 4 repetitions for the right. So we want to divide by 4 factorial. And then there's 4 repetitions for the up. So we also divide by that 4 factorial again. And then if you follow this through, you will get the same answer of 70. Okay, so now I'm going to pass this to Alan, who will go over some more applications.
Okay, hi guys. So we're going to move on to some special cases in prims and columns that you might need to know. So one thing I know that's for sure is probably going to show up is something like a dice roll, right? So you know a standard die has 6 faces, right? So it can be like the numbers from 1, 2, 3, 4, 5, 6. So then let's say you have like a problem where you have, let's say 2 dices, okay? So if you have 2 dices, and then let's say how many ways can you get or can you roll the dice so that the sum in total is like 9, for example, right? So a sum of 9. So we can basically just split it off into, let's say you roll the first dice, which is a 1, okay? And then the second dice, well, it has to be 8, so this case is not possible. Now 2, for the same reason, is not possible, because then your second dice would have to roll a 7, right? And these two cases are actually not possible. So there's only really 3 main cases you have to worry about. It's 3, 6, 4, 5, and then obviously the reverse, which is 5, 4, and then 6, 3. So actually there's 4 main cases we have to worry about. And so essentially there are 4 ways you can roll this dice so that you can have a sum of 9. And so sometimes I'm pretty sure it's not going to be on the diploma, but sometimes if you were to have, let's say, like the probability that this thing occurs, then you would have 6 ways to roll the first dice, 6 ways to roll the second, and then you have 4 combinations where you have a sum of a 9. And so essentially the true probability would be 4 over 36. But since probability is not necessarily on the outcomes of the diploma, they would probably just ask you for how many ways can you, let's say, do a sum of 9. And so the answer here would just be 4. Okay. And so there's a lot of stuff about dice that you can apply to, but the most important thing is to just realize that a die has essentially 6 faces, and each probability of something happening is 1 over 6. So next we're gonna go on coin tosses. So coin tosses is kind of similar idea. Usually it's more so probability, which is again like not necessarily a topic on the diploma. But again, let's say you have 2 coins, right? So as you know, a coin can be a head or it can also be a tail. And so let's say if you flip both of these, what are the chances, or like if you flip both of these 5 times, what are the chances that, let's say, they're both tails or something, right? And so how about this? Let's phrase this question. Actually, let's only have 1 coin, and let's phrase this question so it's like and how many cases, can you guys stop laughing? So how many cases, if you flip this 5 times, that you get at least, let's say, at least 2 tails, okay? So if you flip this 5 times, essentially, there are 2 like outcomes every time you flip the coin, and then you're essentially flipping it 5 times, right? So essentially, what you're doing is you're taking 2 to the power of 5, which is like the total number of outcomes which can happen, which is just 32. Okay, so total is 32. And then so the question was, how many cases out of these 32 are there at least 2 of them that are tails? Okay, so as Jack said earlier, counting like like number of cases where there are 2 tails and 3 tails and 4 tails and 5 tails, that's like pretty tedious. So what we can do is we can take the total number and then we can just subtract the cases that have 0 tails or if they have 1 tail. Okay, so essentially, if there is 0 tails, okay, that means that all of them, all of the times you roll it, it has to be 5 heads, okay? So in order to get a head, well, I guess like there has to be 1, right? There's only 1 case, so 5, so there's only 1 such case happening. Now if you have exactly 1 tail, then what happens is you can have any of the 5 rows be a tail. So it's actually, as Jack said earlier, it doesn't really matter. So like which one of the rows is the one with the head, or sorry, one with the tail. And so it'll be 5 choose 1, okay, times, and then you have essentially 4 cases where it's a head, and then 1 case where it's a tail. So in total, there are 5 such cases happening. And so now you know the number of ways you can get at least 2 of tails happening would be the total, which is 32. Okay, and then minus the number of ways you can get 0 tails, which is just a 1, and then also minus the number of ways you can get 1 tail, which is a 5. Okay, so if you do some quick math, it's 32 minus 1 minus 5, which is 26. Okay, so that means you have 26 ways of getting at least 2 tails out of the 5 coin flips that you're going to do. So again, the most important takeaway here is that essentially you have one way to get a head and one way to get a tail. There are two essentially, two outcomes of flipping a coin, right? So now we're going to move on to what's next? Okay, so we're going to move on to Pascal's triangle. So this is really interesting because the Pascal's triangle has a lot of different properties from everything you learn in perms and coms. No. Yeah, there's no sample space. Okay, so if we do Pascal's triangle, essentially it's kind of the structure of a lot of the combinations that you're gonna do. So what it looks like is it looks like this. We're gonna start from the top with a 1, and then we're gonna basically make it so that the edges are always equal to 1, and then everything below 2 numbers, you're gonna add them to create the next number, okay? So you have 1 plus 1 equals 2. Okay, and then on the edges, you're going to add the ones. Okay, now you're going to repeat, rinse and repeats. So it's 1 plus 2 equals 3, just like so. 1, 3, 3, 1. And then so on and so forth. You have 1, 4, 6, 4, 1. Okay, so essentially this keeps going. Like the Pascal's triangle is essentially infinite. But the most important thing is that there's 2 main applications. So first off, every single term in here is represented by n choose k. So what do I mean by that? If we define this as row 0, okay, so this is like row number 0, then this has exactly essentially 0 choose 0. Okay. Now if we do this as the next row, which is row 1, and we can write this as 1 choose 0 or 1 choose 1. Okay. And also notice that the way I'm writing choose right now is I'm writing it with a bracket. So n choose k is essentially the same as what Jack wrote here earlier with the choose notation. And so here we have 0 choose 0, 1 choose 0, 1 choose 1. And if you just extrapolate this pattern, you just see that this is 2 choose 0, 2 choose 1, and this is 2 choose 2. Okay? So essentially what the Pascal's triangle is you realize that you can use the property where it's like each number is the sum of the previous 2 above it. Okay? So if you have some crazy identity that you have to prove, let's say it's like 20 choose 6, okay, and then plus 20 choose 7 equals n choose k. Okay, let's say this is a question on the diploma, and then you realize that, okay, because according to the Pascal's triangle, I know one thing. So it's the sum of 2 adjacent numbers equals to the one below it. And also, if you write it in terms of n choose k notation, this is essentially the 20th row and also the 7th number plus the 8th number, okay? And so you can think of this in terms of like this. So we have 20 choose 6 as one term of the Pascal's triangle, and then 20 choose 7 is like the term right next to it, okay? And then so you know that this one plus this one, there's also one term right below it, right? It kind of looks like the same thing with the Pascal's triangle. So here, instead of row number 20, it's in the next row, just row number 21. So we know n is probably going to be equal to 21. And then now you're going to think about which term is this term right here. Okay, so if you recall from earlier, let's just say we consider this example. Okay, we have 3 plus 3 equals 6. Okay, so the leftmost 3 here is the second term of this row. This one is the third term of this row, but the number below it is going to be the third term of the next row. So here, essentially, we can apply this rule to this kind of bigger number, where instead of this 20 choose 6, this is 20 choose 7 here. Now, this number is going to be equal to this number in terms of like its position in the row. So 20 choose 7, here it would be the same thing. So it would be 21 choose 7. Okay? So hopefully this makes sense, because then now you can just write it in terms of this n choose k notation. So it would be 21 choose 7. Okay? And so if like on the diploma it's asking you what are the values of n and k, then you would just say it's 21 choose 7. Sometimes it would want you to prove this algebraically. So we can also do that as well. This is kind of like setting up in your head. So what I'm going to do is I'm going to try to prove it algebraically. So the way we do this is we can write it in terms of factorial notation. So as you can see, we can plug in this formula right here. So n is 20 here, and then k is 6. So what we can do is we can do 20 minus 6 factorial times 6 factorial, okay? And then so this is equal to, oh, sorry, I have to do the rest as well. So 20 factorial here, and then here it says 20 choose 7. And so what this is 20 minus 7 factorial times 7 factorial, okay? And so now we can rewrite this in terms of the actual factorials. So we have 20 factorial over 14 factorial times 6 factorial plus 20 factorial over 13 factorial and then times 7 factorial. Great. So now what we can do is we can cancel all the terms that are essentially repeating. So we see 14 factorial on the bottom here and 20 factorial, we can basically cancel this 14 out. And so what we get is we have 20 times 19 times 18 all the way to times 15, because like everything after that, if it's like a 14, it gets canceled out. And so we divide this by 6 factorial, okay? And then plus 20 factorial over, and then the 13 gets canceled out. So actually, this would be 20, well, this would be 20 times 19 times, and then so on until times 14 over 7 factorial. Okay, so basically in order to combine these two fractions together, we're going to multiply this one by 7 on both sides, okay, or essentially the numerator and the denominator. So what we're going to get is we're going to get 20 times 19 times everything to 15 times 7, okay, over 7 factorial, because we added that one term to the 6 factorial. And now we're going to add 20 times essentially the same thing here, times 14 over 7 factorial, okay? And then now that we have a common denominator, what we're going to do is we're going to combine them together. So that's going to be equal to, essentially, so 7 from this one right here, plus 14, okay? Because we can see that everything from like 20 times 15 is going to be repeated, so we can essentially just factor this 7 plus 14 out. And then we have 20 times 19 times everything to 15, like that. Okay, and then now we divide everything by 7 factorial. And so what we get is exactly 21, right? 21 times 20 times everything to 15 over 7 factorial, okay, which is exactly the same as 21 choose 7. Okay, so this is like the completed algebraic proof. If let's say you have the exact same question and then you're looking for how to represent this in terms of n choose k. So looks like that's a calculated representation of what's going on. Okay, so our next topic is going to be cool. So our next topic is going to be binomial theorem. So this is probably one of the most scary theorems if you just look at it. And essentially, the most common form of this is you're going to be asked to either find a certain term in an expansion of like some kind of binomial thing raised to a power, or you're going to try to find like the constant term for this binomial kind of expression, right? So what am I even talking about? You have essentially something, right? So A, okay, plus B, just like so, and then raised that to some power. Let's just call it n, okay? So what is A, what is B? Sometimes A can be like x cubed, sometimes B can be like 1 over x or something like that, and the n is usually just some kind of integer, so like 4, 5, 6, 7, and so on. So there are two applications. I'm just going to erase some of this stuff over here. So one application is you're gonna be asked to find the kth term. Okay. So this first application, find the kth term. So there's a way the binomial theorem works. What the binomial theorem is that, so you have the k plus 1th term, okay, if like k is some kind of integer, so the k plus 1th term is going to be equal to, and you have n from there, choose k, okay, and then times, you have the first thing on the left, which is a, raised to the power of n minus k, okay, and then afterwards we have this times b raised to the power of k, okay, and so this is kind of like the big overarching kind of general idea you want to be thinking about in terms of the binomial theorem. So when we're asked to find the kth term, essentially, let's just say we have an example problem, okay? So let's say we're dealing with a question that's x cubed plus 2x, okay? And then we're gonna find, let's just say raises to the power of 5. And now we're gonna find the third term. How about that? Okay, so third term. And then how we solve this is we're gonna essentially use this formula. So here it's saying the k plus 1th term is all of this. So if we have the third term, which is t3, now what we're gonna do is we're gonna set this equal to the total power, which is 5, total exponent, 5, choose 3 minus 1, which is 2, and then we have x cubed, just like so, which is our first kind of chunk of stuff right here, raised to the power of 5 minus 2, okay? So we're just like, again, following the formula. And then now over here, we have 2x raised to the power of 2, okay? And then so now what you can do is, this is just like a process of simplifying. So this simplifies, 5 choose 2 is equal to 10 times, and then we have x cubed times 3, or sorry, x cubed raised to the power of 3. And as you know by exponent laws, this is equal to x, and then 3 times 3 is 9, okay? And then times 2x squared, so it'd be 2 squared times x squared. And then with some more exponent laws, we get this is equal to 40x11. Okay, so this is going to be the third term of this expansion right here, just like so. So again, a lot of these problems are about applying the binomial theorem directly. The most important takeaway you have to remember is that the tk plus 1 term is going to be used with like n choose k, okay? So if you're finding the third term, you are not doing 5 choose 2 or 5 choose 3. You're actually going to be doing one less than that. So that would be 5 choose 2, okay? So essentially, this is the application of finding the kth term of any binomial expansion. So one other case that's like really hard that we have to know is the constant term. So what this means is, let's say you have a binomial expression similar to this one, okay? But then instead, we're gonna have, let's say x cubed plus 1 over root x, and then let's raise this to the power of 7, okay? And now we're going to try to find the constant term in this expression. So what a constant term means, it just means that like there's no power of x within it, right? So it's just like a number, there's no x involved in it. So what you do is you're going to write out this formula. So we can say let t n be like the constant term, okay? Or like like let tn be the constant term essentially. So we have the formula, so it's tk plus 1 equals, and then we have 7 choose k, okay? And then we define this tk plus 1 term as the constant term, okay? So essentially that would be 7 choose k times x cubed raised to the power of 7 minus k, just like so. And then now according to the formula, we also have this other one. So 1 over root x. Okay, so 1 over root x, just like so, is raised to the power of k as well. So now we know that essentially we can rewrite this so that this 1 over root x is an exponent form. So here it's 7 choose k times x to the power of, and now we can just distribute this according to exponent laws. So this is 21 minus 3k over here. And then here we have 1 over root x, okay? So if you think about it, it's like root x is x raised to the power of 1 over 2, right? And then you have 1 over, so it's like x raised to the power of negative 1 over 2, just like so. So negative 1 over 2 raised to the power of k, according to exponent laws, is negative 1 over 2k. Okay, and then afterwards, essentially we know that we have to produce a constant term. So this is like the really big keynote you have to remember for constant term is the value of x, okay? Whatever it is, it has to be raised to the power of 0, okay? So this is the main term that you have to focus on, is it has to be equated to x to the power of 0. So whatever this chunk of stuff is right here, this has to be equal to x to the 0. So let's do it over here. We have exponent laws, so 21 minus 3k, and then plus essentially what is here, so negative 1 over 2k equals x0. Great. So as you can remember, x0 is just 1. Now we can equate this exponent right here equal to 0. So we have 21 minus 7 over 2k equals 0. So 7 over 2k equals 21, and then k equals 6. Great. And so sometimes if you mess up in this problem, you'll realize that this k value might be greater than the 7 you had initially, which is like this exponent. So if anything like that happens, it's like you realize that, oh, maybe I'm doing something wrong, because this k value should always be between the values of 0 to 7. Okay, so now we have this nice value of k equals 6. Now we're going to find the constant term. So we're going to save ourselves some time. We know all of this is equal to 1. Okay, so we can essentially ignore all of this right here. And then we have the 7 choose k value left. So what we're going to do to find the constant term is we're going to just go plug in k equals 6 into 7 choose k, and that's going to be your final answer right there. So tk plus 1 equals 7 choose 6, just like so. Okay, and 7 choose 6 equals what? 7 choose 6 equals 7. So that's going to be our final answer, and this is going to be the constant term of our expression. Okay, great. So this is pretty much the hardest thing you'll be asked to do in prims and columns. This is like probably the hardest application of the binomial expansion. So again, just to recap, oh, I actually forgot to erase this. But so the first one is find the kth term, which is like find some term of this expansion. And the second one is finding the constant term for some kind of binomial expansion. And so again, what you do is you just use the formula, plug it in, and then solve for the point when x is equal to, or like this value for x is equal to x raised to the power of 0. And then so what you do is you find the value for k, which that works, and then you would just solve for the term and then find whatever constant is left when you divide everything, or if you remove everything from right here. Right, so I think that's all for prims and columns. That is pretty much, huh?
We love you, Alan.
Oh, so that's pretty much all there is for prims and columns, and that's pretty much all you need to know. Really?
Circular.
Oh, there is circular.
Just it's really quick.
Just
though.
do it really fast.
Okay, so and then really quickly, I forgot there's one last topic we have to talk about actually. It's circular stuff. So what that means is, let's say you have a circular arrangement of chairs. Okay. Actually, let's use the same example that Jack went over earlier. So we have 7 friends. Okay. But then the issue is, instead of 7 chairs being arranged in like a horizontal line, you have this circular kind of orientation of chairs. Okay. So like it's like 1, 2, 3, 4, 5, 6, 7. Okay. So the issue is, let's just say we try to apply the approach that Jack taught earlier. So there's 7 ways to put it into like this chair, for example. And then one next to it has like 6 ways, and then 5, and then 4, 3, 2, 1. Okay. And normally you would think this is good. Like normally you would think, oh, okay, now we have this many ways to arrange it. But then you realize that the circle can be rotated. So here's the problem. Let's say instead of choosing this one to be first, and then you basically shift this entire circle like 1 unit like clockwise, so that everybody is in all these different positions. And so now you essentially have created the same thing. It's still the same orientation, right? So essentially we're overcounting by a lot here. Now, how do we fix this problem? Okay, so essentially what we've done here is 7 factorial, right? So putting 7 people into 7 seats, we don't care what's going on. And then if we do care, now the issue is you can put any of these 7 rotations, we can rotate it 7 times, and there's still going to be the same rotation, right? So all we have to do is do 7 factorial and just divide it by 7, okay? Because there's like 7 rotations around the circle. And so 7 factorial over 7 is equal to 6 factorial, which is equal to 720. Okay, now there's also the scenario, let's say you're making a bracelet, okay, and then you have 7 different colors, okay, you have 7 different colors of, there are 7 different colors of like those beads you can put onto your bracelet. And then so the issue is a bracelet can not only be rotated in kind of like this XY dimension, it can also be flipped over. So the issue with that is we have, again, 7 factorial. Now, we've said earlier that the order kind of like does not matter when you rotate the circle. So divided by 7, because there's 7 ways to kind of rotate the circle. You also have to divide for the case when you physically flip the entire bracelet over. Okay, so there's two ways you can do so. And so it'd be 7 factorial over 7, and you also have to divide this by 2 as well for 2 orientations. And so 7 factorial over 7 over 2 is equal to 6 factorial over 2, which is equal to, if you put this into your calculator, is equal to 360. So there's 360 ways to create a bracelet with 7 colors. That's all. So you really just have to be careful if it's asking for, if it's like in a straight line, or if there are ways in which they can maybe be repeated. So let's say, for example, a circle, or it's like a bracelet, or some kind of circular arrangement of chairs. So great. I think that is final for Math 30. That is pretty much all you need to know for the diploma. Great. So now we're going to have a quick general tips and Q&A section for the diploma. So
Hello, everyone. Are there any questions on any topic?
you can also ask us like, what are the contents that you think might be covered in a different course, let's say like AP or IB, but then like you're not sure if it will be included in the diploma. So you can ask us those questions as well.
I think the chat is dead.
Question? Yeah. Guys, please reply.
Oh, there's also a slight delay. Oh, my laptop.
So as we're waiting for the questions, we're also just going to give you a few general tips on the diploma. Okay.
Edward, go turn around my laptop. And now we can see the.
Did you make it big?
Not yet. Other way around, though, so we can see it. Switch over to your.
I'll give the general tips. Okay, so one really interesting tip that we've heard from previous alumni and some teachers is that when you're writing the diploma, think about it. If it's like 9 a.m. in the morning and you're opening the test booklet, what you should do first thing is you should go to the writing section and then finish the writing first. So the reason why you do this is because the writing section is generally harder and requires more thinking than the multiple choice section. And so by doing so, you're essentially using most of your brain power first. And then by the time you kind of think about all the topics and you're like, oh, I remember this topic, or I know how to use this log rule now. And then now you can go back to the multiple choice section, and that's where you can start to go through everything there, and that's going to make your overall time kind of management easier, and it's also a better way for you to remember all the stuff you cover during your prep. So yeah, that's the first tip we have.
Number 2, please sleep and do not wake up at 7 a.m. while going to bed at 2 a.m. on the day of the exam. What will you do on the diploma? Well, based on the fact that you watched us just now, and also because the diploma is actually quite a bit easier than you would expect. Like, all you have to do really, you're given 6 hours. Take your time. Don't freak out. The night before, get like a good night of like, I don't know, get like a good 8 hours of sleep at least. Don't sleep too much, otherwise you're gonna like feel groggy and like tired throughout the exam. But like sleep enough. Make sure you drink water. Make sure you like eat. Don't go in on an empty stomach. That's gonna distract you, make you not very make you not think very well. And then just like review a little bit, review a bit of everything. You have 6 hours. If you're struggling, you have time to like try and remember it back. You have some time to try and like figure it out by yourself. And most importantly, you have time to like play around with your calculator until you get a number that seems correct. What does this mean? It means that you will get 100. So yeah.
Yeah, thanks, Jack. So the best tip that I have, I know this might not work for everyone, but basically like before your test, just like do some form of physical exercise because it does improve your mental clarity when you're doing the diploma. So basically like just before you go, like do a couple push-ups, run a couple laps around your house. I mean, anything is fine as long as it gets those like creative juices flowing, you know? Any more questions? Tip.
Oh god, it's gonna die. Okay. Don't be like me and not. Don't be like me and make sure your calculator is charged. Because you don't really want to go in with a dead one because that's kind of a big part of the exam. Yeah, really use your calculator because at the end of the day, like you do have access to it, so exploit the use of it because it genuinely will be very, very helpful. And just like make sure you know how to use it because is like regression gonna be on it? Now regression is not going to be on it, but you can still like graph all your questions, like make sure you check your x values and all of that. Yep.
Okay, and also one final tip is like you should honestly bring a small sugary snack to munch on during the diploma. So it's like it's okay to be a little bit big, but the thing is like you have a little bit of sugar, and what that sugar does, it like allows you to think better and with more clarity. Okay. so so essentially what that does is like it's okay, but usually most test taking centers is like you need to have all your snacks in like a clear plastic container, so like make sure that's happening. But it's okay to just generally bring a little bit of food. And it's also like when you're stuck on a question, you can just like eat a little bit and then just give yourself a bit of time to think about the question, and then hopefully that can make you remember some very critical information that you might forget. Yeah.
All right, any more questions? Oh yeah. Okay, any more questions? Guys, I think chat is dead. It's okay. No. We'll just chill now. We'll just chill. No, don't close the stream. There's 15 viewers. Okay, thanks for coming.
Okay, guys, I cannot stress this enough, but like you really have to before the night before exam. Like generally, don't cram. Like if you're gonna cram the day before, so that you at least get some good night's sleep. Okay, so like if you normally have a really bad sleep schedule and you're sleeping at 3 a.m. every single day, okay. So
Okay,
so
this guy sleeps 2 hours every single. This guy sleeps 2 hours every single day. I don't know how he survives. I don't know how. Like, what are you running on? What are you running on? What are you running on?
I'm running on like 2 hours of sleep. Okay, but anyways, that's like the most important tip that you can give. And it's also a good general tip for any test you're going to be taking in the future, not including the diploma. But if you're taking like an AP exam or an IB exam, the same rule applies. So really get some good sleep. I cannot stress this enough. Okay, so if there are no more questions, we're just gonna wait for a few more minutes and just chill. And then we're gonna be ending the stream at 4:30, I believe. Oh, there's actually quite a lot of time until 4:30. We're actually gonna end the stream at 4 p.m. So
First person to type in the chat wins 1 cent from you. I'm just trolling on stream.
Did we tell them about what you guys were doing last week?
okay, also, for anybody who might be reviewing this diploma stream, for the people who are taking this diploma in semester 2, a lot of the same tips apply. So like usually there's not much of a difference between the semester 1 diploma and the semester 2 diploma. And so just make sure to review everything like a good solid week before, so that you're solid on the concepts, and just don't cram the day before. Yeah. Before y'all go, can I give problem request?
Also, the breakdown of the diploma is like is 75% multiple choice and numeric, right? And then 25% written, and the majority of it is the functions and relations that we covered, and then there's a little bit of trig and a little bit of logs. So that's the breakdown, and we find that a lot of the questions are like related to. They're a lot how do you describe them?
What money at?
Hmm?
Oh no, never mind.
We find that a lot of the problems are a lot like they can be tricks, but you also just have to make sure that your mind is like clear. So that's why we recommend a lot of sleep. Okay.
I think we should give more general feedback on like general things.
All you.
Okay. Hi guys. Okay, wait. I don't think I should say this.
Mr. Chess with Latios, what is your question?
Guys, chain reaction.
Chain reaction. Right. So actually, that's like terms and cons, right?
Oh, it's like dependent events.
Oh no. So like you guys know physics, right? So like we're like transmission of energy or something. I don't know. So like there's an object, right? Goes this way with like a momentum. What's the units for momentum again? So let's say that I have a 1 kilogram object. We have a 1 kilogram object, right? Traveling at what momentum? Wait, P equals mv. Mass. Wait, is it mass times? Oh, so it's newtons. Wait, no. Oh, it's joules per second. Okay. Right? You collide with another 1 kilogram object, right? And then there's another 1 kilogram object here, right? So the idea is that when these two collide, right? You you get how does this work? So assuming no friction, right? Assuming no friction. Newton seconds, okay? So like the idea is like when they collide, they each have the same momentum. Cause like oh wait, no, do they have the same impulse? Yes, no, they have the same impulse, right? They have the same impulse. So let's say this has 1 Newton second. Wait, are you sure? Yeah. So wait, 1 Newton second. Impulse should be the same. This is 0. So wait a second. So like this thing collides. What? What? Wait, how does this work? So wait, when they collide, right? After they collide, this goes 0. So let's say this is x, right? Oh yeah, fusion. So actually, real question. Fusion, right? Hold on. So a fusion reaction. Hold up, I need this clipped here. So fusion. Oh no, maybe I did. Okay, so basically, I learned fusion like just a couple of days ago, aka on Friday. Like literally 10 minutes before the test, but I still understand it very, very well. So fusion, right? You have two hydrogens. They collide together very, very fast, right? Very fast. Under conditions where there's like high temperature, and high pressure, right? Or, it's the same, right?
Density and pressure?
Oh no, okay. No, density. No. They are the same. Okay, you know what? High squishiness. I don't know. Okay, I'll just use squishiness. So if there's high temperature and high squishiness, they will collide with such a great force that the idea is like the nucleus also goes like boom, right? So what's the nucleus again? So there's a proton, right? There's another proton. They collide. Oh wait. Well, oh wait, no. Okay, hydrogen cycle, right? Wait, 1 plus 1. You get deuterium, right? 2 1, but then you also get a gamma ray. It's this thing. No, you don't get a gamma ray. You get a beta particle. And that should be. Is it beta positive? Is 0 1 0 1? Yes, thank you. And then you also get a neutrino. No, you get a neutrino, right? And then the deuterium, right, collides with the hydrogen to make helium. And then in this process, a gamma ray is released. And then the last part is two helium things go kaboom. And then they make a helium 4. And then two hydrogens. And this is the proton-proton cycle, which releases, if I remember correctly, 26.7 mega electron volts of energy. So actually, this process is very, very important because like fusion is like creates energy, right? And energy is good because it allows us to do stuff. So actually, I would like to introduce you to my new idea, a fusion-powered cooking stove. So here's how we're going to accomplish it, right? We're going to take a sample of the sun. And then we're going to transplant it. Like you learned in bio, right? You can transplant stuff, right? So we're gonna take the sun, right? We're gonna take the eukaryotic cell, and then we're gonna transplant it into the cooking stove. And the idea is that the mitochondria, because they're the powerhouse of the cell, can undergo fusion. So when they undergo fusion, wait, guys, stop laughing. This is a very serious matter. Okay. So they can undergo fusion, right? So if we have one mitochondria, we can denote it using the symbol M. So a mitochondria has one mass but zero charge. So in that way, we can also represent it as a neutron. So you have two neutrons, right? When we combine them, what ends up happening is the opposite of pair annihilation. We split up the particles to get two hydrogens and two antineutrinos, right? So the antineutrinos can be extracted using let me see this. Can use osmosis, right? Let me see. So now that we have two hydrogens, right, we can use the mitochondria to create hydrogen, which in turn can fuse together under sufficient conditions to create energy, right? 26.7 mega electron volts for each reaction. Now that is a crazy amount of energy. Yes, it is. 26.7 megavolts. Mega electron volts. I know, but hear me out, right? Using this power, if enough reactions are performed, eventually you can get so much power, right? Think about it. Why does the sun emit so much radiation? That's because it undergoes fusion, which has 26.7 mega electron volt energy production, right? And that's why the sun is so powerful. And that's why by transplanting the eukaryotic cells of the sun into the cooking stove that we've designed before, if we're able to do that, we can create a fusion-powered stove that can truly change the world. I'm looking... what's something I need to discuss in reference to this? Nationalism, you're right. So nationalism. So nationalism, wait, is the screen? No, don't. Don't kill it. Can they see me? No, don't. I swear. No, do not kill it. Do not kill it. No, nationalism, right? What is nationalism? So nationalism is when Alan tries to steal my microphone and tries to silence me. Why are you trying to silence me? Why are you silencing me? Why?
Okay, guys. Okay, guys, so... Oh, sorry for the loud.
You do not have that power.
Jack! Okay.
Under Mill's utilitarianism,
So basically, thanks for coming for the Diploma live stream. We hope you have the best of luck in the Diploma live stream. Oh wait, what am I saying? We hope you have the best of luck studying for the Diploma. And so, yeah.
Everyone in this stream will get 100. Trust.
Ah!
Mic drop.